The atmosphere is defined as being the gaseous envelope surrounding a celestial body. In more simple words, the atmosphere is the collection of gases that is held around the Earth by gravity. There are various major gases that make up our atmosphere. The most common gas is nitrogen, which accounts for about 78% of the atmosphere. Oxygen is sometimes misconceived as being the most abundant gas, but it represents only 21%. Just under 1% is argon, with carbon dioxide and a few others making up the rest. There are many more gases that are found in such small quantities that we regard them as trace gases. Some of these include neon, helium, methane, ozone and hydrogen. Water vapor is another gas in the atmosphere. It's found in very small quantities, but without it, there would be no weather. So much of our understanding of weather is to do with the behavior of water in our atmosphere. It can become visual to us in many ways, such as clouds, rain, snow, hail, frost, and so on. The relative amounts of the gases stays fairly constant up to about 60 kilometers above the Earth. Thereafter, gravitational separation alters the composition of the atmosphere. However, there are other changes, primarily in temperature, that allow us to structure the atmosphere into segments. The first of these segments, or layers, is called the troposphere. This layer is closest to the Earth, and its defining characteristic is the marked decrease in temperature with height throughout the layer. Where the temperature no longer decreases with height defines the upper part of the troposphere. This upper boundary we call the tropopause. Here, temperature is constant with altitude. The thickness of the troposphere, and therefore the height of the tropopause, is not constant across the Earth. Over the poles, the height of the tropopause is about 8 kilometers, whereas over the equator, it's about 16 kilometers. The average height is 11 kilometers, which is found at about 45 degrees latitude. What controls the height of the tropopause is the general temperature of the troposphere. As a general rule, the colder the troposphere, the lower the tropopause, and vice versa. The extremes of this are demonstrated very well over the poles and the equator. It follows that when the troposphere is at its coolest, i.e. over the poles in winter, then the tropopause would be at its lowest. However, there are places where the tropopause folds or breaks. This is where we find a significant difference in the temperature in the troposphere, and therefore a significant tropopause altitude change. The first of these is at about 40 degrees latitude. The warm air circulating from the equator meets much cooler air circulating from mid-latitudes. This temperature difference in the troposphere causes a height change of the tropopause. The second tropopause break is at higher latitudes of about 55 degrees, where polar air meets tropical air. This happens along the polar front, which we'll talk about much later on. Again, there's enough of a temperature difference within the troposphere to cause a tropopause height change. The last of the tropopause breaks occurs at even higher latitudes, and is evident mainly in the northern hemisphere and in winter. This is where very cold Arctic air meets less cold polar air. It occurs typically at about 60 to 70 degrees latitude. The temperature difference here is also enough to cause another tropopause fold or break. If we know that temperature decreases with height, then it follows that the closer the tropopause is to the Earth, the warmer it will be. Over the poles, the tropopause temperature is about minus 50 degrees Celsius, and over the equator, it's minus 80 degrees Celsius. As we can see, at the tropopause, temperature increases with latitude. Of course, this is the opposite from what happens at the surface, where temperature decreases with latitude. Why is the tropopause so important to us? Well, the tropopause signifies the start of a marked temperature inversion. This effectively limits the vertical movement of air and clouds within our atmosphere. It's useful to know, then, that the tropopause usually signifies the limit of cloud development. However, the tropopause does tell us other things. As a result of very low densities in the upper atmosphere, the upper winds tend to be very strong, and in some cases form narrow bands. These are called jet streams. These in themselves can be beneficial if our flight goes in the same direction. But with these jet streams there is a likelihood of significant turbulence. We call this clear air turbulence, or CAT. Having discussed the troposphere and its upper boundary, the tropopause, we'll now look at the next layer in the atmosphere, called the stratosphere. The stratosphere extends from the tropopause up to about 50 kilometers above the Earth's surface. The temperature structure of the stratosphere is dominated by the presence of ozone. Ozone is formed when solar radiation splits oxygen into its two individual atoms. These are then free to combine with others to form the gas ozone. This process releases energy into the surrounding air, and therefore heats up the part of the atmosphere where ozone can be found. Concentrations of ozone are at a maximum at around 20 to 25 kilometers above the Earth's surface. Due to latitude effects and the depletion of ozone during the polar winter, the temperature through this part of the stratosphere can vary from -30 to +20 degrees Celsius annually. Superimposed on the Earth is a colour representation of ozone depletion. The purple area over Antarctica is showing where we have the greatest amount of depletion. This is due to a number of reasons, and the discussion of this is outside the scope of this lesson. Where the temperature starts to fall again signifies the top of the stratosphere and marks its upper boundary. This boundary is called the stratopause. Above the stratopause is a much cooler layer where the temperature continually decreases with height. This layer is called the mesosphere. It usually extends about 80 or 90 kilometers above the Earth's surface. At the top of this layer, we have some of the coolest temperatures encountered, sometimes as low as -180 degrees Celsius. The upper boundary to the mesosphere is called the mesopause. Above the mesopause is a layer called the thermosphere. This zone is characterized by a rapid rise in temperature up to about 200 kilometers. Temperatures here can be between 600 and 2000 degrees Celsius. The lower part contains a zone called the ionosphere, where we can have such high ionization levels that long-wave radio waves can be reflected back to Earth. Where this reflection is at a maximum is at roughly 110, 160 and 250 kilometer levels. These are respectively called the Kennelly, Heaviside and Appleton layers. The upper part of the thermosphere is known as the exosphere. This layer starts at about 700 kilometers above the Earth's surface and is highly tenuous and undefined. All the layers we have analyzed have been defined by their unique temperature profiles. However, most of our flying and our weather is contained within the first two layers of the atmosphere, namely the troposphere and the stratosphere. Within these two layers we have many properties which are important to us, like density, pressure, and temperature. However, our atmosphere is so very variable from day to day, it's been necessary to construct a model atmosphere for help in calibration of instruments and aircraft testing. This model atmosphere is known as the ICAO International Standard Atmosphere, or ISA, sometimes referred to as ISA. However, the model only extends to 32 kilometers, which is about 105,000 feet above mean sea level. ISA assumes that, at mean sea level, the temperature is 15 degrees Celsius, pressure is 1013.2 hectopascals, and the density is 1,225 grams per cubic meter. From the surface, up to 36,090 feet, or 11 kilometers, the temperature decreases at a constant rate of 1.98 degrees Celsius per 1,000 feet, or by 0.65 degrees Celsius per 100 meters. The temperature decreases down to minus 56.5 degrees Celsius. This is where we find the tropopause in ISA, and the temperature no longer decreases with altitude. From this point onwards, we have the stratosphere, and ISA assumes the temperature within the first part of this layer remains constant at minus 56.5 degrees Celsius up to 20 kilometers, or 65,617 feet. From 20 kilometers and upwards to 32 kilometers, we have a gradual increase in temperature by 0.3 degrees Celsius per 1,000 feet, or 0.1 degrees Celsius per 100 meters. If you remember, this is the part of the stratosphere that contains the gas ozone, which causes the surrounding air to warm. All aircraft instruments are calibrated to ISA. Therefore, it's essential to know just how much the actual atmosphere on a given day differs from ISA. The simplest method we use to analyze this difference is through comparing the real temperature to the standard ISA temperature. This is known as the ISA deviation. In other words, how much the real atmosphere deviates from the standard atmosphere. Let's recap the ISA lapse rate within the troposphere. Remember, we said ISA assumes that the sea level temperature is 15 degrees Celsius. The temperature then fell by 1.98 degrees Celsius per 1,000 feet. In the diagram, we can see that at an airfield 1,000 feet above sea level, the ISA temperature should be 13.02 degrees Celsius, but the actual temperature is 20 degrees Celsius, which is much hotter than the standard. We need to calculate how much hotter than ISA the real atmosphere is. A simple mathematical calculation shows that the atmosphere is 6.98 degrees Celsius hotter than ISA. The representation of this information is important. The best way to understand it is by reading the ISA deviation backwards. We can say that the real atmosphere is 6.98 degrees Celsius hotter than ISA.
Pressure is well known to be a fundamental part of meteorology. Many years ago, scientists saw a strong relationship between the distribution of pressure and the weather. This led to one of the simplest instruments called the barometer, which many households use for ornamental purposes. These were developed well before the 19th century and are still used today. Over the years, more complex instrumentation has been developed to measure atmospheric pressure to the degree of accuracy required for aviation. The forces generated by horizontal pressure differences give rise to horizontal air movement and therefore winds. The vertical variation of pressure gives us the ability to measure the height of an aircraft above a surface. The instrument that measures this variation is the altimeter. As pressure is reduced with height through the atmosphere, the altimeter will read a higher value. As you can see, pressure is fundamental to meteorology and aviation. This lesson aims to give you an understanding of pressure in our atmosphere and its significance to us as aviators. What is atmospheric pressure? The air in the atmosphere is made up of particles, and as a result, these will be subject to gravity that will tend to pull the particles downwards. Therefore, any area on the Earth's surface will have to support the weight of the column of air directly above it. This weight is otherwise known as atmospheric pressure. The less air in the column, the less the pressure will be at the surface. The higher and higher we go in the atmosphere, the total amount of air overlying us decreases. Therefore, the less the weight of air above, the less the atmospheric pressure. So, pressure decreases with altitude. We will now look at how pressure is measured and represented in meteorology. As we mentioned earlier, traditionally, pressure was measured using an instrument called a barometer. There are two types, an aneroid barometer and a mercury barometer. A mercury barometer consists of an inverted glass tube of mercury with its open end inside a reservoir at the bottom. When high atmospheric pressure is experienced, the force or weight of the atmosphere will depress the mercury in the open reservoir and force more of the mercury up into the tube. This displacement is traditionally measured in inches. The higher the column of mercury, the higher the atmospheric pressure. The other type of barometer is non-liquid and is therefore called an aneroid barometer. These can be less accurate than mercury barometers, but are more sensitive to small changes in air pressure. An aneroid barometer measures the effect of air pressure on a metal chamber, from which part of the air has been removed. Changes in air pressure make the chamber expand or contract, moving a needle on a dial. The dial may be scaled in millibars, inches, or millimetres. These light and portable barometers are widely used in homes, offices and schools, and importantly for us, in aircraft. Often, a special type of aneroid barometer, called a barograph, is used to record changes in atmospheric pressure over time. A barograph includes a pen that records the air pressure on a paper chart mounted on a rotating drum. Going back to the mercury barometer, once calibrated, the average sea level pressure will displace the mercury from the level in the reservoir by 29.92 inches. The United States usually use inches for measuring pressure. However, elsewhere it is more common to use the millibar, or hectopascal, to measure atmospheric pressure. This uses a different scale, but for comparison, 1013.2 hectopascals is equivalent to 29.92 inches of mercury. In recent years, the adoption of the metric hectopascal has been replacing the millibar. However, do not worry because the hectopascal and the millibar use the same scale. 1013.2 millibars is also 1013.2 hectopascals. In summary then, 29.92 inches of mercury is the same as 1013.2 millibars and 1013.2 hectopascals. Remember from the atmosphere lesson that this is the atmospheric pressure at mean sea level according to ISA. Next, we will look at horizontal variations in pressure. Now we need to analyse how we might show pressure variations across a region. This is important because then we will be able to identify if one area of a surface is experiencing higher or lower pressure than another area. In order to remove the pressure height anomaly, i.e. the vertical pressure variation, we reference our observations to a common horizontal level, usually mean sea level. If we look at the diagram, we can see various stations reporting their particular pressure values. If we now draw a line connecting all the areas with the same pressure, we end up with a pattern of lines over the surface. These lines are called isobars, and they join places of equal pressure. Using these pressure values, we can identify areas of low and high atmospheric pressure. Lower value isobars indicate a low pressure. A concentric low value enclosed isobar shows the lowest pressure and reveals the center point. These systems can range from tens of nautical miles wide to hundreds and even 1,000 miles wide. Note, though, that the spacing between the isobars in the low can be smaller than those found around high pressures. This means that the pressure gradient, or the change in pressure with distance, can be greater within a low-pressure system than in a high-pressure system. By watching the isobars change shape over time, we can see how these systems behave. If they were to intensify or deepen, we would see new concentric lower value isobars appearing within the central part of the depression. If the isobars move outwards from the centre, then the depression is growing outwards and covering a wider area. If we see low pressure isobars protruding outwards from the low pressure into an area between two highs, we call this an isobaric trough. As you can see, isobars are a very useful way of visualizing pressure patterns and hence the weather. Next, we will take a look at high pressures and how they are depicted. Basically, a high-value isobar indicates a higher pressure. An enclosed high-value isobar shows the highest pressure within an area and reveals its centre. As mentioned previously, note that the isobar spacing in high pressures tends to be further apart than the low-pressure systems. We will return to this point again shortly. By watching the isobars, we can see over time how high pressures can change. New concentric higher value isobars developing in the centre of the high indicate the high pressure is intensifying. If the isobars around the high were moving outwards, we could see the high pressure is growing. If we see the isobars protruding outwards from the high pressure into an area between two lows, we call this a ridge. It signifies an extension of the high pressure into another area, spreading its influence. Looking at the chart, it is possible to identify areas which are not high or low pressures. These areas are generally found between highs and lows and are called cols. They are synonymous with calm conditions. High pressures, low pressures and cols are dealt with in considerable detail later on. Knowing where high or low pressures exist is a fundamental part of meteorology and safe flying. High and low pressures determine the movement of air horizontally, and to a lesser extent, vertically. The horizontal movement of air is more simply understood as wind. The vertical movement of air is a major contributor to the formation of clouds. So, as you can see, understanding these pressure systems is an important part of meteorology, and as such, will be discussed in more detail later on. We have talked about how these pressure systems can move and develop over time. This can be presented on another type of chart, and instead of using isobars, we use isalobars. These lines join places of equal pressure change, or tendency, during the 3 hours preceding the time of observation. These charts are very useful in showing how rapidly the pressure is changing in an area. Regions of falling pressure are shown by closed concentric negative value isalobars. These are called isalobaric lows. Conversely, regions of increasing pressure over time are shown by closed concentric positive value isalobars. These are called isalobaric highs. The knowledge of pressure change becomes important later on, once we have an understanding of the significance of falling or rising pressure. Returning back to the surface pressure charts with isobars, we mentioned earlier in the lesson that there tends to be different spacing between the isobars in high and low pressure systems. The spacing of these isobars is significant and will tell us information about the strength of the pressure variation in a region, and hence the wind strength. This relationship is very similar to contours on a map. The spacing of contours on a map tells us information on the gradient of the land where mountains and valleys are located. We know that tightly spaced contours show a very steep gradient or slope. Similarly, isobar spacing shows the pressure gradient. Tightly spaced isobars show a very steep or strong pressure gradient. We call this force the pressure gradient force, or PGF. A large pressure gradient force means that there is large pressure change over a small area. The pressure gradient is important because it controls the velocity of air, such that if the isobars are tightly spaced, there is a large pressure gradient force and therefore strong winds. Going back to pressure systems, remember that generally in high pressures, the isobars tended to be further apart than in low pressures. This means high pressure systems have less of a pressure gradient and are therefore associated with lighter winds than low pressure systems. This concludes the analysis of horizontal pressure change. We will now look in more detail at the variation of pressure with height. Earlier on, we saw that pressure decreases with height in the atmosphere. In fact, it decreases at a decreasing rate. However, pressure does not decrease everywhere at the same rate. This is because temperature affects the pressure lapse rate of the atmosphere. Cold air has a tendency to cause pressure to change more rapidly over a given height than warm air. Looking at the diagram of the atmosphere from a side view, we can see that pressure is decreasing with altitude. We start at the surface at 1,000 hectopascals and reach 300 hectopascals at 30,000 feet. However, When the air on the left is cooled, we can see that the isobar levels start compacting and sinking towards the cold air. This has the effect of reducing the pressure at any given height. Look at the pressure now at 30,000 feet in the cold air. It is no longer 300 hectopascals. You can see the pressure is much less now. We can summarize to say that cold air causes isobars to compact in the vertical, increasing the pressure lapse rate and reducing the pressure even more at any given height. Now let's look at how warm air changes the pressure lapse rate. When the air on the right is warmed, we can see that the isobar levels start expanding away from the warm air. This has the effect of increasing the pressure at any given height. Look at the pressure now at 30,000 feet in the warmer air. It is no longer 300 hectopascals. You can see the pressure is much higher now. In summary then, we can say that warm air causes isobars to expand in the vertical, decreasing the pressure lapse rate and increasing the pressure at any given height. It is important to note that pressure is still less than at the surface, but depending on the temperature of the air, the relative pressure at a given height in cold air will be less than in warm air. The fall of pressure with height can be seen in the table. Note that pressure decreases at a decreasing rate through the atmosphere. A height change of 5 kilometers near the surface reduces the pressure by approximately 473 hectopascals, whereas a height change of 5 kilometers above 25 kilometers reduces the pressure by only 13.6 hectopascals. The values in the table correspond with ISA. We have just seen that changes in temperature and pressure at any given point in the atmosphere affect the pressure change with height. This pressure lapse rate as we know it will change markedly if temperature variations in the atmosphere exist. In the previous example, we have seen how the pressure lapse rate changes with height. An alternative view is to see how height change varies with a given pressure value. In other words, what increase of height corresponds with a fall in pressure of 1 hectopascal. There is a numerical method of calculating the vertical height change per hectopascal. The formula is shown in the diagram. When the variables are inputted into the formula, the result will show the height, in feet, represented by 1 hectopascal change in pressure. The variables are temperature in Kelvin and the pressure in hectopascals. The value 96 is a constant. Let's now see the result of inputting the ISA conditions at mean sea level. For the value of T, remember ISA states that at sea level the temperature is plus 15 degrees Celsius. To convert to Kelvin, just add 273 to this value. Now we have 96 multiplied by 288 degrees Kelvin. The pressure at mean sea level, according to ISA, is 1013.2 hectopascals. The result now shows that a change in pressure of 1 hectopascal at sea level in ISA represents a height change of 27 feet. Let's now observe the result if the temperature is changed. Remember that if we cool air down, the isobaric surfaces or pressure levels compact. Therefore, a change in 1 hectopascal will represent a smaller height difference. If we now insert a reduced temperature of 260 degrees Kelvin, as opposed to 288, then a change in 1 hectopascal now represents only 25 feet, not 27 feet, just as expected. Again, we can confirm that cold air increases the pressure lapse rate. The implication of this temperature effect on pressure variation is very important in producing accurate pressure information. We have seen that pressure varies in 2 dimensions, horizontally and vertically. To understand how pressure varies horizontally, we would have to remove the vertical pressure variation. As a result, we would have to assume a level horizontal surface. Pressure values which are not on this common surface will have to be adjusted to it. This common level is usually mean sea level. However, as we know, not all surfaces are at mean sea level. Looking at the diagram, we can see a location approximately 1,000 feet above mean sea level. How do we then calculate what the sea level pressure might be? We know that the sea level pressure will be higher, but by how much? This will surely depend on the vertical pressure lapse rate. But we have just demonstrated in the previous scenes that different temperatures will give different pressure lapse rates. If the air at the location was colder than ISA, we would expect the pressure lapse rate to be greater. So when adjusting the surface pressure to mean sea level, we would gain more pressure in 1,000 feet than if the air was warmer than ISA. The 2 diagrams confirm this for us. The diagram on the left shows that if a station was above mean sea level and the air was colder than ISA, the corrected mean sea level pressure would be higher when compared to warmer than ISA. These mean sea level pressures are known as QFF values. QFF is therefore the barometric pressure at a stated location, corrected to mean sea level, using the prevailing temperature. How are these values used, though? Well, firstly, they are plotted on charts, and then lines are drawn, joining places of equal values. These lines, as we already know, are called isobars. Isobars on surface weather charts are therefore derived from QFF values. These surface pressure charts are commonly seen in weather broadcasting and weather briefing information. As you can appreciate, pressure is fundamental in meteorology and aviation. Throughout this CD-ROM, pressure is mentioned and discussed many times. It is important to understand what it is and what affects it. In the lesson on pressure systems, you will see how important horizontal pressure variation is in understanding weather and wind. In the lesson on altimetry, you will see what significance the vertical pressure variation has on aircraft operations and procedures.
Density is defined as mass per unit volume. In other words, how much material is inside a given space. Density can be expressed in many ways. The first way you've already seen. This is grams per cubic metre, or, in standard international units, kilograms per cubic metre. If you remember from the lesson on the atmosphere, we talked about the standard atmosphere, or ISA. At sea level, ISA stated that the density was 1,225 grams per cubic metre. So we have a mass, which is 1,225 grams, in a volume, which is 1 cubic metre. However, there are other ways in which density can be expressed. If we know the standard sea level density in ISA, Then we can use this as a benchmark to compare densities from other areas. So we take the density of 1,225 grams per cubic meter as 100%. If another area has a density of only 1,000 grams per cubic meter, then this density is approximately 82% of the ISA surface density. We call this expression of density relative density. We are comparing the density in one area relative to the density in ISA at sea level. Another way density can be expressed is by using the term density altitude. Trainee pilots seldom understand this term, but it is essential, especially when using it to discuss aircraft performance. However, before we analyze this term, let's first look at the two main variable factors that can influence density. These are temperature and pressure. Looking at the diagram, we can see the density formula. Notice that in the formula, we replace density with the Greek symbol rho. We'll now look at how the variables of temperature and pressure affect the mass or volume, and therefore the density. Let's first look at how pressure can change density. If we look at the diagram, we can see a mass within a volume. As we increase the pressure surrounding the parcel of air, you can see that it gets compressed. This causes the density to increase. We're keeping the mass the same, but reducing the volume. Conversely, if we reduce the surrounding pressure, the parcel will expand and the density will reduce. Again, the mass is the same, but this time the volume has been increased. Physical experiments confirm that density is proportional to pressure. The other main variable we mentioned that controls density is temperature. Looking at the diagram, we can see that as we heat a parcel of air, the particles get excited and cause the parcel to expand. This reduces the density. The mass is staying the same, but the volume of air is increasing. Conversely, if we cool the parcel down, it will shrink and the density will increase. Again, the mass is remaining the same, but we are reducing the volume. We can therefore say that density is inversely proportional to temperature. Having seen the effect of varying temperature and pressure on density, let's now consider the effect of altitude on density. Here we have a conundrum. As altitude increases, temperature falls. Therefore, density should increase. But as altitude increases, pressure also falls. This causes the density to decrease. So what does happen to density with altitude? The overriding effect is the change of pressure. The reduction of pressure reduces the density more than the reducing temperature causes density to increase. Since pressure is the dominant effect, it follows that because pressure decreases at a decreasing rate with altitude, so will density. Looking at the diagram of ISA, we can see that relative density decreases with altitude at a decreasing rate. Having seen the effect of density with altitude, let's now consider how density changes with latitude. Looking at just the surface conditions, we can compare the poles to the equator. From the diagram, we can see that at the poles, the temperature is generally colder, and the pressure generally higher than at the equator. The combined effect is that at the surface, the density at the poles is greater than at the equator. However, at altitude, the effect is different. If we remember from the pressure lesson, we stated that cold air increases the pressure lapse rate with altitude. In other words, pressure falls more rapidly with height in cold air than in warm air. Because density is strongly linked with pressure, it therefore follows that in cold air, density would decrease more rapidly with altitude than in warm air. As a result of this, over the poles where we have cold air, the density at a high flight level would be much lower than at the same flight level over the equator. At high altitudes, we can say that density decreases with latitude. There is one more variable that can alter the density of air. This variable is water vapor. The effect is complicated and beyond the scope of the expected level of knowledge needed. It's sufficient just to know that the density of water vapor is less than dry air, such that if a parcel of air was to contain water vapor, the density would be less than that of a parcel of dry air. If you remember from earlier in the lesson, we mentioned density altitude. Having seen the effect of all of the variables on density, the expression of density altitude can now be better explained. Density altitude is simply defined as being the altitude in ISA that the prevailing density would occur. This is best explained by using an example. Let's say we're at sea level, and the atmosphere happens to be exactly the same as standard. The density at sea level in the real atmosphere will therefore correspond exactly to that found at 0 feet in ISA. However, now let's increase the temperature of our location at sea level. We now know that the density will be less. This new lower density at our location corresponds to a density found at a higher altitude in ISA. In our example, we can see that the density at sea level in the real atmosphere equates to a density found at 10,000 feet in ISA. We therefore say that the density altitude of our location is 10,000 feet. The knowledge of density altitude is important in assessing the effect of the changing density on aircraft performance. We'll cover this later, but for now, let's see how we can calculate our density altitude. There are two simple ways of calculating the density altitude. One method is by using a flight navigational computer, and the other is by using a simple numerical formula. This formula states that for every 1 degree Celsius away from ISA, depending on whether the deviation from ISA is positive or negative, you add or subtract 118.8 feet to your pressure altitude to find your density altitude. Now let's look at an example. Let's say the pressure altitude is 2,000 feet and the temperature is 25 degrees Celsius. This means the atmosphere is 13.96 degrees warmer than ISA. Therefore, the ISA deviation is plus 13.96 degrees Celsius. We can now see that the density altitude is 3,658 feet. Most density changes are accounted for in performance graphs by the use of altitude and temperature nets. The example shown is the landing distance graph for a small single-engine aircraft. We'll now look at the importance of density changes on aircraft operations. One of the most fundamental effects of density is on the lift that an aircraft can generate. Looking at the lift formula, we can identify density by the Greek symbol rho. With all other variables remaining the same in the formula, you can plainly see that a reduced density would decrease lift. So, for a given speed, the lift generated would be less. This has many implications on aircraft performance and can cause increased takeoff distances, reduced payloads, reduced engine power, and so on. It's therefore essential to take into account the prevailing density, so that any changes in aircraft performance can be identified and calculated. We generally must remember that in high, hot, and humid areas we'll have a reduced density, and therefore poor aircraft performance. Be very careful not to exceed the limitations of the aircraft, and accurately account for altitude and temperature effects using the aircraft manual.
We saw in Lesson 2 that pressure can vary across the surface of the Earth. The understanding and identification of this is very important. By knowing where pressure variations exist, we can make assumptions on the movement of air vertically and horizontally. The types of pressure systems we find across the Earth are principally depressions, low pressure or cyclones, and their counterpart, anticyclones or high pressure. There are features called cols we shall also look at later. The first of the pressure systems we're going to look at in detail is probably the most significant to us: depressions, or as they are more commonly known, areas of low pressure. These will be discussed in two ways. The first will deal in small-scale low pressures, and the second with much larger-scale low pressures. The first of these depressions, the small-scale lows, can be found almost anywhere on the Earth's surface, and are created when a column of air is warmed from below. Air lying on top of a warm surface will be heated by that surface through conduction. This air will then become warmer and less dense than its surroundings. This will cause it to rise. The rising air will travel up through the atmosphere and eventually diverge when reaching higher altitudes. The total weight of the column of air above that warm surface has been reduced because it is now comprised of much warmer, lighter, less dense air than the surrounding cooler areas. The result of this is a reduced pressure at the surface. If the surface pressure drops, then the air will naturally be drawn towards the centre of the depression. As this air travels in towards the low from the sides, it too will be heated and rise up into the atmosphere. We can then summarise that in these small-scale depressions, air converges near the surface and then rises. These small-scale depressions are sometimes referred to as heat lows. Now we have seen what the airflow is doing inside these lows, let's briefly look at what the weather conditions might be. Let us consider a parcel of air. As it rises, it will expand. This is because the pressure of the surrounding air is falling. Less resistance is therefore offered against the walls of the rising parcel. This expansion will make the rising air cool as it ascends. The process is called adiabatic cooling and will be covered in detail later on. If the air is cooling as it rises, then condensation may take place when the air temperature reaches dew point. These water droplets can be seen as clouds. The clouds that are created will take on a vertical appearance as the air is rising. We call these cumuliform type clouds. Cumulus clouds tend to give showery precipitation, as opposed to continuous precipitation. The type of precipitation is usually rain and sometimes hail, because they tend to be heavier than the force of the rising air and will therefore fall due to their own weight. What we will look at now are the problems that pilots may experience when encountering such systems. We have so far seen that the weather has been created from the rising air. However, it is a little more complicated than simply this. If we look at the airflow surrounding the system, we can see a recirculation of air, and outside the cloud, we can identify descending air. This is further complicated when precipitation is falling. The precipitation will drag air with it and cause downdrafts within and underneath the cloud. These up and down drafts, both within and surrounding the cloud, can be a potential problem to aircraft. If a pilot were to fly through these systems, the aircraft could be exposed to significant amounts of turbulence. The stronger the depression, the greater the potential for turbulence. The symbols used to report turbulence are shown in the animation sequence. Another phenomenon significant to pilots is icing. This is where liquid water, or supercooled water, freezes onto an aircraft's frame. This dramatically affects the aircraft's performance and flying capability. Don't panic though, it is discussed in much more detail later on. Let's go back now to our small-scale heat low. If the aircraft was flying through this weather system above the freezing level and liquid water was present, it could lead to aircraft icing. These low pressures involve very active uplift, allowing significant vertical support. Therefore, huge quantities of large supercooled droplets can be suspended within the cloud. It is the combination of significant quantities of water droplets and a temperature of 0 to -15 degrees centigrade that gives the icing risk. As operators of aircraft, we need to be aware of the potential for moderate to severe icing conditions in cumuliform cloud. The symbols for reporting icing are shown in the animation. One other important weather situation is the horizontal visibility near the Earth's surface. If we know air is converging and rising, then surely any impurities near the surface will be drawn up into the upper atmosphere, leaving much clearer air on the surface. We can generally say that in a small-scale heat low, the surface visibility should be good, except, of course, when there is precipitation. So far, we have stated that these types of depressions are generally on a small scale of maybe tens of miles. However, under rare circumstances, these depressions can become the largest, most powerful and destructive weather phenomena on the surface of the Earth. These are called tropical revolving storms. They are known more commonly as hurricanes, cyclones or typhoons. They can be over 700 nautical miles wide. Because of their scale, the spin of the Earth becomes important. The winds are deflected as they enter the centre of the depression, causing rotational speeds up to 200 miles per hour. These unique depressions will be discussed much later on. Now we need to talk about the other type of depression, the large-scale low pressures. These are otherwise known as polar frontal depressions. They are created in a very different manner than the small-scale heat lows. The polar front depressions are found along the polar front itself. This is principally in the higher latitudes, at about 40 to 60 degrees, depending upon the season. They typically move from west to east across the globe. The process of their formation is complicated and a little involved. Essentially, there are two main processes that need to occur to create a mature polar front depression. The first is to do with upper air movement, associated with fast currents of air, called jet streams. If we look at an example in the animation, we can see that the flow converges and narrows. This narrowing causes the velocity of that airflow to increase. The effect of this is complicated, but it is sufficient to say that as a result of this, there are areas where we have net loss and net gain of air in the upper atmosphere. These can be split into zones, labelled A and C. In the areas labelled C, we have a net loss of air. In other words, air wants to leave this location horizontally. In this instance, air tends to leave the upper atmosphere more quickly than it is replaced by air from lower down in the atmosphere. It is this net loss of air in a particular column that causes a reduction in pressure at the surface. As a result, air will ascend from the surface to the upper level, around area C. The second main process occurs nearer the surface and needs to work in conjunction with the upper air process that we have just described. Within the temperate latitudes, we have warm tropical air, meeting much cooler polar air. The boundary between these two different air masses is called the polar front. As with any boundary between two liquids, this will not be a continuous straight line. At some points along the front, we will find kinks, which are small irregularities along the front. What is happening in these kinks is that the warm tropical air is intruding into the cooler polar air. As the image sequence shows, this causes the warm air to replace cold air. This is an important point. If much lighter, warmer air replaces the colder, heavier air, then the surface pressure will drop, because we have reduced the total weight of the column. This particular process occurs quite regularly along the polar front. However, if this occurs underneath one of the upper air C zones, then the kink will develop further as warm air continues to replace cold air. This will eventually lead into the formation of a large-scale polar front depression. If we now look at the fully developed depression from above, we identify two unique surface features. The line with blue triangles on it identifies the first feature. This is called a cold front. This is where we have cooler, heavier air advancing and undercutting the warmer, lighter air. The advancing cold front will cause some of the warm air to rise up and over the cold air, but also force it to move, much like a bulldozer. The movement of this warmer air creates the second important surface feature. The line with the red semicircles on it identifies this second feature. We call this a warm front. This is where we have lighter, warmer air overriding heavier, cooler air. The warm air between these two fronts is called the warm sector. Its characteristics control the weather within the depression. If you remember from earlier, the low pressure was created from the intrusion of this warm air into the cold air, thereby reducing the surface pressure. Because this is essentially one of the main driving forces of the depression, some analysts have called these lows warm sector depressions, not polar front depressions. The movement of air, and therefore the wind within these depressions, is very different to the small-scale depressions. By knowing what the wind conditions are, we can better prepare for our flying. If the surface pressure is falling in the centre of a depression, then it goes to follow that air must move in horizontally. This is similar to the small-scale depression. However, what is different is that the surface flow doesn't quite get to the centre of the low directly. It appears to have a rotational flow around the centre as well, exactly like that of the tropical revolving storm. The reason that there is rotational flow around the low pressure is due to the Earth's spinning. The spinning or rotation of the Earth will cause air moving into the low to be either deflected to the right in the northern hemisphere or to the left in the southern hemisphere. This apparent force creating this deflection is known as the Coriolis force. It is sometimes referred to as the geostrophic force. In summary, we can say that air moves around these large-scale low pressures anti-clockwise in the northern hemisphere and clockwise in the southern hemisphere. Now we have seen how the air flows around such large-scale systems, let's now see what we might expect the weather to be like. The depression weather can be subdivided into the warm front and the cold front. Looking at the cross-section of a polar front depression, let's now take a look at the warm front, since it will be this part of the depression that will arrive first. We stated earlier that at the warm front we have warm, moist air being forced to rise over and above cooler, denser air. As this air rises up and along the front, the temperature will drop because of adiabatic cooling. This may cool the air to the dew point and condensation will occur. As a result, clouds will form along the front. Because the slope of the warm front is so shallow, roughly 1 in 150, the clouds that are developed have a broad horizontal appearance and are therefore more commonly stratiform cloud. This means layered type. These clouds can extend up to 600 nautical miles away from the surface position of the front. Looking along the front, note that at lower levels the cloud is much thicker and denser than those at higher levels. Therefore, if a warm front were to approach an area, we would see the cloud lowering and thickening. Firstly, we would notice the thin cirrus cloud at very high altitude, then the thicker cirrostratus, followed by the lower altostratus, and finally, right before the front approaches, the larger, thicker nimbostratus. This is one of the most obvious ways of recognizing an approaching warm front. As a result of the slope of the front and the horizontal spread of the cloud, the precipitation would cover a very wide area in front of the front, maybe a few hundred miles. As the front got closer, we would encounter increasing amounts of precipitation. This may be light and intermittent at first, but just in front of the warm front, where the cloud is lowest and thickest, we may encounter much heavier, continuous precipitation. The type of precipitation is another important point. Because the air along the front is rising relatively gently, there is only moderate vertical uplift. It is therefore common to find a mixture of fine rain and drizzle, or perhaps snow if the temperature is low enough, falling ahead of the warm front. In special cases, freezing rain or rain ice may fall, but we shall look at this later. Other important issues for aviation are the icing and turbulence that may be encountered along the warm front. The icing will generally be light along the warm front because of the lack of vertical support. However, with orographic intensification, the vertical support is increased and the freezing level can drop. Under these circumstances, the icing can be very dangerous. It is essential then to analyse your location to point out potential intensification. Under special circumstances, the most severe form of icing can be found underneath the warm front. This is known as freezing rain or rain ice, but as we mentioned earlier, this will be discussed in detail within the icing lesson. Turbulence along the warm front can be explained in a similar manner to icing. Because of the lack of vertical motion, the horizontal passage of an aircraft through the warm front would not abruptly change. We would most probably expect moderate turbulence within the lower clouds and light turbulence within the higher clouds. Finally, we will look at the surface horizontal visibility. Precipitation intensity increases as the front approaches, from light drizzle underneath the outer stratus clouds to eventually moderate or even heavy rain beneath the nimbostratus at the front itself. Because of this, the visibility will decrease significantly as the front approaches. Fog can also be found before the front approaches, sometimes 200 nautical miles ahead of the front. This is known as frontal fog, and will be discussed in detail in the visibility lesson later on. The next section to look at will be the warm sector. Within this area of the polar front, we can generally find low cloud, such as stratus and stratocumulus, and occasionally advection-type fog. The reason for the cloud is because the warm air has come from the tropics. Therefore, it has had to pass over cooler land and waters. As a result of this, the bottom part of the air mass, which is in contact with the surface, will be cooling, and the air will be condensing, creating the cloud and fog. However, this is only happening at the surface. The rest of the warm sector above hasn't been cooling, and would therefore be mostly clear of cloud and weather. The next main weather of the polar front depression is the cold front. We stated earlier that at the cold front we have cold air undercutting warm air. The warm air is being forced to rise over and above cooler, denser air. As this warm air rises along the front, the temperature will drop because of adiabatic cooling. This may cool the air to the dew point and condensation will occur. As a result, clouds will form along the front. The slope of the cold front is a little steeper than the warm front. This slope is still quite shallow, and the clouds created by the rising air would still be layer type. But there is an important difference. When looking at the cold front at the surface, we see the front comes forward first, then starts to slope backwards. This nose of cold air is up to about 9,000 feet. This creates a unique effect. When cold air is found above warm air, that area can become very unstable. This means that the air has a potential for strong vertical movement. Convection will take place if the warm air rises into the cold air. This warmer air will now be much lighter than the air surrounding it and will rise just like a balloon. Therefore, we could find vertical or convective cloud concealed within the layered cloud. It is quite common to find large cumulus, cumulonimbus, or even thunderstorms embedded within the cold front. These are potentially dangerous clouds to aircraft operations, and the weather on the cold front will now be discussed. The precipitation on the cold front will be varied because of the mixture of cumulus and stratiform cloud. So not only could we get intermittent and continuous precipitation, but most probably some heavy showers and even hail from the convective cells. Associated with these heavy showers, we might get some strong gusty winds as the air is dragged down towards the ground by the precipitation. Even at altitude, we would have to be very careful indeed. The turbulence could be quite severe, especially within the convective cells along the front. It is much the same with icing. Generally, light to moderate icing would be experienced, but within the convective cells there might be increased vertical support. This would enable greater quantities of large supercooled water droplets to be suspended. This could lead to severe icing within the convective cloud. Let's now look at what visibility we might expect. At the cold front, within areas of the precipitation, the visibility would be poor, especially within heavy rain. But outside the precipitation, we might find good surface visibility. This is due to the convective currents extracting air contaminated with pollutants such as dust and smoke. Lastly, we look at the weather behind the cold front. Air here has come from higher oceanic latitudes and will generally be cool and relatively drier than the warm sector. However, the air here is moving towards the equator and therefore travelling towards lower, much warmer latitudes. This will warm the lower layers of the air and cause it to become less dense and rise, or, as we can say, become unstable. This instability leads to convection and so the formation of cumuliform clouds. As we have seen, this convection leads to showery precipitation, with possibly hail as well. Again, turbulence and icing could be a problem within these areas. This now concludes the breakdown of the polar front depression. We can see that looking at the main weather within polar front depressions, there is a lot of information to absorb and understand. The weather is complex and variable, but by breaking down the weather and the aviation hazards into the warm and cold fronts, hopefully you will have a better understanding as to what is going on. We will cover these depressions again in a separate lesson, and all these points will be recapped later. Depressions of any kind will change through time and be of various shapes and sizes. By analysing the pattern of the isobars, it is possible to identify the shape of the low pressures. If we can see the isobars forming a finger-like protrusion away from the centre of the low, then we call this an isobaric trough of low pressure. Trough weather can be as active and occasionally even more active than that of a main depression. Looking at the diagram, the surface winds tend to converge along the trough line. This results in a convergence zone that encourages the air to rise. This convergence zone can be very active, and areas of convergence need to be monitored very closely for potential weather. The weather around these troughs is very similar to that of the main depression itself, with all the potential problems of cloud, precipitation, icing, and turbulence. There is another type of surface trough that is caused by upper air processes. These are known as trough lines and are represented on charts with a solid black line. These troughs are significant and have weather that is very similar to the cold front with active cumuliform clouds. This brings to a close one type of pressure system, namely the low pressures. But if you remember, the other major pressure system we need to look at is high pressures, or anticyclones. To generate a high pressure at the surface, the weight of a column of air must be increased. In other words, there must be a net gain of air to the column. As the surface pressure increases, air will move outwards and away from the high. This will cause a general descent of air towards the surface. This is sometimes referred to as subsidence or sinking air. We can now summarise that air within a high pressure descends and diverges. This movement can be achieved in two main ways. These different ways define what type of high pressure it is. The first types are called permanent warm anticyclones. The reason for the name is because they tend to create very warm, dry surface conditions. Let's look at the reason why. If you remember back to low pressures, we stated that if air was forced to rise, it would cool adiabatically. In this type of high pressure, the reverse is the case. In the upper atmosphere, we can have an excess of air. Therefore, air will be forced to descend towards the ground. As this happens, the air is compressed under the increasing amount of pressure, and this causes the temperature to rise. We call this adiabatic warming. When the air eventually reaches the surface, it can be relatively warm. But remember, the reason for the high pressure was because of a net gain of air in the upper atmosphere. If we look at a global picture of the Earth, and then briefly examine the major air circulation patterns, we can find areas where we have an excess of air in the upper atmosphere. In the areas highlighted, you can see air is converging in the upper atmosphere, creating a net gain of air. The air then descends and warms. We find these warm anticyclones between the Hadley cell circulation of air and the Ferrel circulation of air. These high pressures form two bands around the Earth, from about 20 degrees latitude to about 45 degrees latitude. They form what is known as the subtropical oceanic high pressure belt. This belt will move north and south with movement of the sun, moving to higher latitudes in summer and lower latitudes in winter. The subtropical highs tend to give very stable, fine weather. The reason is relatively simple. In order to create cloud, condensation must take place. Therefore, air must be cooled to dew point. However, in these high-pressure systems, air is sinking and warming, and therefore condensation is prevented. This means that any significant cloud development is very unlikely. This has an additional effect. Outside the summer months, when we have long nights, the Earth cools quite substantially, especially when there is no cloud. Even though the air could be quite dry, the temperature may fall enough during the night so that the dew point is reached. This would cause condensation and cloud to develop on the surface next to the cold land. We call this radiation fog. It can be quite a common feature with high pressures, especially in winter and spring, and is more often seen in the morning. The small islands found in the oceans underneath the subtropical highs demonstrate the warm, fine weather that we would normally expect within the warm anticyclones. The weather in these areas is hot, very dry, and of course clear of any cloud. Classic areas are the Azores and Bermuda highs in the North Atlantic. Over the land, though, because of the extremes of temperature and lack of moisture, we find our major deserts. There is another way to generate a high pressure and for air to descend. If the land surface is very cold, then this will cool the layer of air in contact with it. This will in turn cool the layer of air immediately above, and so forth. These layers of air will slowly get heavier and heavier and sink as this cooling continues. The result is a gentle, widespread subsidence of air, creating a cold anticyclone. These anticyclones are very common over large land masses in winter, where the ground cools very rapidly compared to the sea. These are apparent especially in Siberia and North America during the winter months. These areas can have extremely low temperatures with clear, very frosty skies. The cold anticyclones are also found over the poles, creating the polar highs. They tend to be weaker though, and other systems can pass through and disturb their development. The final type of anticyclone is one that is more transient, smaller in size and of short duration. As such, it is termed a cold temporary anticyclone. In fact, this anticyclone is really a ridge of higher pressure found between two polar front depressions. It is temporary to a person under its influence, since the ridge will move with the polar front as it travels from west to east. If we just discovered that within the high pressure there will be little or no cloud, then surely we would expect little or no precipitation. It goes to say that if there is very little chance of any water droplets, let alone any supercooled ones, then the risk of any icing is fairly slight. Because the descent of air is relatively widespread, it is unlikely that any significant vertical movement of air will develop to disturb aircraft. We can therefore say the risk of any low-level turbulence is minor. Next, we shall look at the visibility we might find within high-pressure systems. In warm anticyclones in particular, we have large-scale descending warm air. However, there is a layer very close to the Earth which is unaffected by this warm descent. As a result, this layer of air will be cooler than the warm air above. This creates a temperature inversion. These are known as subsidence inversions and mark the point where temperature abruptly rises with height instead of falling with height, which is normally the case. This causes the layer to be very stable, and as you will see in the next scene, this has a significant impact on the visibility. If we know that large amounts of air are being drawn down towards the surface, surely then any particles from industry and agriculture will be held against the surface. The visibility over land would therefore deteriorate whilst the high pressure was dominating the region. Sometimes, whilst on the climb out from an airfield, you can notice the top of this poor visibility layer. This is a very good indication of the subsidence inversion. The movement of air within an anticyclone is also of huge importance to aviation. We already mentioned that air is descending at the centre of an anticyclone and then diverges outwards along the surface. However, the high pressures are of such a large scale that the wind along the surface is deflected by the Coriolis force. If you remember, it deflected winds to the right in the northern hemisphere and to the left in the southern hemisphere. In summary, we can say that air moves around high pressures clockwise in the northern hemisphere and anti-clockwise in the southern hemisphere. Notice here that the isobars are widely spaced, indicating light winds. By analysing the pattern of the isobars, it is possible to see the shape of the high pressure. If we can see the isobars forming a finger-like protrusion away from the centre of the high, then we call this a ridge of high pressure. Ridge weather is usually identical to the weather found within the main high pressure. Air is still descending and diverging. Having seen the two main pressure systems and their weather in detail, we need to analyse the last of the pressure systems, coals. A coal is quite special in that it represents an area not directly under the influence of either a high or a low pressure system. In fact, it is the region in the middle of two lows and two highs. Note that within this region, the isobars are very widely spaced. Because of the wide spacing of the isobars, the wind found within a coal is very light and variable. Other than the wind, the weather within a col is dependent somewhat on the season. Generally, over land areas, we can say that in summer typical col weather would be thundery, whilst in winter it is mainly very foggy.
In the lesson on pressure, we saw the fundamental relationship pressure had with altitude. If you remember, we said pressure decreases with altitude. This relationship is what the altimeter will use to determine height. We've already seen how the altimeter works, but let's just recap its fundamental points. It's an aneroid barometer, and therefore uses the principle that changing air pressure will cause a small chamber to expand or contract. This chamber is linked to a pointer rotating over a scale graduated in feet or meters. If we look at the diagram, we can see that a fall in outside pressure will cause the chamber to expand and turn the pointer clockwise. An increase in pressure will do the reverse. This time the chamber is compressed, causing the pointer to move anti-clockwise. Now we've seen how it works, let's put it into practice in the atmosphere. We said pressure would decrease with height. Therefore, as our aircraft climbs through the atmosphere, the pressure will decrease and the altimeter pointer moves clockwise, showing an increase in height. Conversely, when the aircraft descends through the atmosphere, the pressure increases and the pointer moves anti-clockwise, showing a decrease in height. There's one problem. The altimeter is reading a height, and we've seen that this increases as we climb and decreases as we descend. But what is this height value measured from? If the altimeter needle is pointing at 10,000 feet, what are we 10,000 feet above? The ground? The sea? The airfield, or what? This is what the altimeter cannot tell us. What we must do is find out from which level the altimeter is assuming 0 feet. In fact, this is not an actual geographic location. It's a pressure value. The altimeter has no idea where it is in terms of objects like land and sea, but what it does know is where it is in relation to different pressure values. We can tell the altimeter what pressure to start from, but not what physical place. This is done by means of an adjustable subscale. This is a small window in the face of the altimeter, which has a pressure value, either in hectopascals or inches of mercury. Whatever pressure value is set in this scale, it's the pressure at which the altimeter will assume 0 feet. Looking at the diagram, we can see that a pressure of 1,000 hectopascals is set within the subscale. Therefore, if the altimeter was at this pressure level, then the needle would read 0. As we climbed, pressure would decrease from this value, and the altimeter would show how far away it was from this pressure level. Notice that the value within the subscale is not changing. It's simply reminding us what pressure value has been set as the datum. Our initial problem has still not been solved. We need the altimeter to give us a height above a physical surface, not a pressure surface. We can solve this by having a variable subscale. In other words, we can manually select what pressure the altimeter will use as a 0 point. This scale is adjustable from 850 to 1050 hectopascals. Let's work through an example. If we place the altimeter on our airfield and set the subscale to the actual pressure of the airfield, then our altimeter will not only tell us how high we are above that pressure level, but also how high we are above the airfield. In other words, it will tell us our height above the ground. Getting the altimeter to read height above the airfield can be very useful to the pilots if operations require accurate height above the airfield. If we were to get the actual pressure of the airfield and correct it to the airfield reference point or threshold, then we have a pressure value known as QFE. If this pressure was set within the subscale, the altimeter would read 0 when on the ground at the threshold or airfield reference point. If the aircraft was then to climb, the altimeter would show the height above the airfield. This can only be useful within the immediate confines of the airfield. Looking at the diagram, we can see that if we were to fly 5 miles away, the altimeter will still read the height above the airfield. Notice that because the ground is uneven, we no longer have a reading that tells us how high we are above the ground in our immediate vicinity. This is not very useful, and could lead to potential problems, especially if we are unable to see the ground. As we have seen, QFE has its limitations, and is only useful in some instances. As pilots, we are not always interested in how high we are above the airfield. In some instances, we may wish to find out our altitude above mean sea level. This would tell us our elevation from mean sea level. This can be valuable, since terrain and obstacles are also shown as elevations from sea level. It would make our clearance of obstacles much simpler to calculate. However, in order to do this, we would have to insert the pressure value found at sea level into the subscale on the altimeter. If you remember from the lesson on pressure, we saw that the QFF was indeed a sea level pressure value. Surely, if we could insert the QFF value into the subscale, the altimeter would read our elevation above mean sea level. However, there is a problem with using QFF in altimetry. In calculating the pressure at sea level from any given location, QFF takes account of the effect that the prevailing temperature has on the pressure lapse rate. Indeed, this is vital in order that we can accurately calculate sea level pressure to produce charts. This is where we have a problem. The altimeter works on a pressure lapse rate according to ISA. It has no idea that temperature deviations from ISA will cause a varying pressure lapse rate. It has been specifically calibrated to ISA. What we must do is calculate the sea level pressure from a location using a standard atmosphere. This is known as QNH. However, QNH will never actually measure the true sea level pressure unless we have a completely standard atmosphere. QFF will always provide a more accurate sea level pressure. Let's work through a few examples of how QFF and QNH will differ under different atmospheric conditions. In this first example, let's assume that we have a station pressure of 920 hectopascals, 300 meters above mean sea level. The temperature at the airfield is minus 20 degrees Celsius. The airfield is obviously a lot colder than ISA. The pressure at sea level will obviously be much greater, but by how much? Let's work out QFF. In correcting the pressure to mean sea level, QFF will account for the fact that cold air will increase the pressure lapse rate. So QFF will read a higher value at sea level than normal. QNH will also work out the mean sea level pressure, but it will not know that the pressure lapse rate is greater because the air is colder. QNH assumes an ISA atmosphere, so QNH will not gain the same amount of pressure that QFF did. We cannot have two different pressures at one location. Since QFF is the most accurate method, we will assume the real sea level pressure to be that of the QFF. Because the QNH value is not as high as QFF, it will be found just above the real sea level. If QNH is set on the altimeter, and the aircraft is at the real mean sea level pressure, the altimeter will read below zero. Summarizing, we can see that at locations above mean sea level, in a colder than ISA atmosphere, QFF will be greater than QNH. Let's take a look at how we might calculate the sea level pressure when we're actually below sea level. In this example, let's say we're 50 meters below sea level with a station pressure of 10-20 hectopascals and the outside temperature is 30 degrees Celsius. Since sea level is above us, it must be a lower value than 10-20 hectopascals. The fact that warm air reduces the pressure lapse rate is recognized by QFF. The pressure is not reduced by much when calculating sea level pressure. QNH, on the other hand, does not know that conditions are warmer than ISA, and it uses a higher pressure lapse rate, reducing the pressure by much more. So, in 50 meters, to find the QFF, the pressure was reduced by a lot less than QNH. In this example, below sea level in warmer than ISA conditions, QFF was more than QNH. However, different pressures cannot exist at the same level. So since QFF is the most accurate, it will remain at the real mean sea level, and QNH pressure will be found slightly above mean sea level. Lastly, here is a summary diagram to show the relationship of QNH and QFF in all conditions. Even though QNH does not accurately measure sea level pressure unless the atmosphere is ISA, we have to use it as mean sea level because our altimeter is calibrated using ISA conditions. We will, of course, be in error, and later in this lesson we'll see how to calculate this error. From now on, let's assume that QNH is mean sea level pressure, even though we know otherwise. With QNH set on the subscale, the altimeter should read the elevation of the airfield when the aircraft is at the airfield reference point, elevation being the height above sea level. When we're flying, we refer to the indication of the altimeter as an altitude whenever QNH is set. QNH is more useful on cross-country flights because it provides a height above sea level, which is similar to the way our terrain is displayed on maps. There is only one problem with QNH. The calculated value of QNH was from an airfield pressure at a location. What happens if the pressure changes along our route? Pressure changes along our route creates quite significant problems. Looking at the diagram, we can see we have obtained a QNH of 1020 from the airfield and subsequently climbed to 270 feet. We shall maintain this indicated altitude all the way on our flight towards the airfield on the right. To maintain a constant indicated altitude, we would have to ensure that the pressure surrounding the altimeter will not change. To do this, we must in essence follow an isobar. If the QNH at our departure airfield was the same as at our destination, the isobars would be roughly parallel to the true horizontal. But look at what would happen to the isobars if the QNH was lower at the destination airfield. You can see that the isobars now slope towards the ground. En route to our destination, we must ensure our indicated altitude remains the same. But in doing so, we're actually travelling closer and closer to the ground. So, our true altitude is getting less and less, but our indicated altitude is remaining the same. We have a saying to alert us to this problem. When flying from high to low, look out below. Our altimeter eventually overreads our true altitude. We can shorten the statement to be high, low, high. High to low, altimeter reads high. This is not a good situation if we can't see the ground. Unbeknown to us, we are actually descending in relation to our true altitude. Let's look at another situation. Watch what happens if the destination QNH is higher than our departure airfield. Notice that the isobars now slope upwards. If we were to maintain a constant indicated altitude, we would have to follow those isobars upwards. This time our true altitude is getting higher, but our indicated altitude is remaining the same. We can say then, from low to high, the altimeter reads low. Low, high, low. This situation is not too dangerous, since our true height is increasing, but nevertheless, it's not accurate flying. What these principles show is the need to constantly adjust the pressure setting on the subscale to account for variations in horizontal pressure. Notice that the altimeter now reads a more correct altitude than before. This resetting of the subscale is a vital part of aircraft operations. When taking off or landing at an airfield, the controller will give us the correct QNH, which we must confirm we have understood by reading it back to him correctly. We must then adjust our subscale accordingly.
Golf Alpha Bravo Charlie Delta, 6 miles west, descending height 1,000 feet, request joining information.
Golf Charlie Delta, runway 02, QNH 1006, 3 aircraft in the circuit.
Runway 02, QNH 1006, Golf Charlie Delta.
This will ensure our altimeter is not only reading correctly, but is reading the same as other aircraft within the vicinity. However, this procedure only solves the error on departure or arrival at an airfield. En route, our altimeter would still be in error. How do we ensure that en route we have the most up-to-date pressure in the region in which we are flying? This problem is solved by the provision of regional pressure settings, called RPS. The map shown here allocates areas where RPS values are issued. These areas are known as altimeter setting regions, or ASRs. When flying into these various regions, the altimeter should be reset to the values provided by them. This will again ensure a more accurate altimeter reading, and also ensure everyone else is on the same pressure setting. However, even if we have the correct setting within a region, on approach to an airfield, the controller will still ask us to set the airfield's QNH, because it may be slightly different. The reason for this is that the RPS value is valid for 1 hour based on the lowest forecast QNH within the region. Our airfield will most probably have a slightly higher pressure value and be more up-to-date than the RPS value. On a long flight at high altitudes, changes in the pressure will impact us less, since we are usually far from the ground. Continually changing the pressure setting in the subscale can be tiresome. As a result of this, we revert to a constant pressure setting. This is called the Standard Pressure Setting, or SPS. In the United Kingdom, this occurs when the aircraft climbs through 3,000 feet, when QNH is set on the subscale. This is known as the transition altitude. When passing through this altitude, we must set the standard pressure setting of 1013 hectopascals on the subscale. From this moment on, we refer to the indication on the altimeter as a flight level or pressure altitude. However, the transition altitude is not always 3,000 feet on QNH. For example, within the London TMA, it is 6,000 feet. In some countries, the elevation of the airfields can be greater than 3,000 feet. In this case, the transition altitude is usually a set height above ground level. Always be sure to check the transition altitude at unfamiliar airfields. When descending to an airfield, there will be a need to reset the altimeter back to QNH again. This point is known as the transition level. The transition level is not fixed and varies over time and place. As a result, air traffic will tell us at what level we should change from 1013 to QNH. Even when 1013 is set on the subscale and we are flying at high altitudes, we will still experience increasing or decreasing true altitudes as pressure varies horizontally. However, at such high altitudes, the change is almost insignificant. There is one final pressure setting. It is seldom used, and it is unique to very high altitude airfields. This pressure setting is known as QNE. It's defined as the height indicated on landing at an aerodrome when the altimeter subscale is set to 1013.2 hectopascals. This definition is only pertinent to those airfields where the normal QFE range can't be selected on the subscale. In other words, the QFE pressure values are outside the range 850 to 1050 on the subscale. We'll now look at what will happen when changing from one pressure setting to another. This is best demonstrated using a diagram. Let's say we have an aircraft with the airfield QNH of 1030 set on the subscale, and the aircraft is climbing through the transition altitude of 3,000 feet. The pilot will have to change the subscale to 1013. Notice that as the pilot changes the subscale, he is changing the zero datum point. As a result, the altimeter pointer will show a decrease in altitude as it moves anti-clockwise. Let's look at it another way. Now we have an aircraft which is descending through the transition level on approach to an airfield. The altimeter subscale would be set to 1013, but the pilot has been told by the air traffic controller that he must select the QNH, which is 1020. Notice that this pressure level is further away from the aircraft, and as a result, the altimeter's starting point is much lower. So, as the pilot adjusts the subscale, the altimeter will respond by showing an increase in altitude. However, it may be necessary to quantify these changes in pressure to actual values in feet. For simple calculations below 5,000 feet above mean sea level, we use a height change of 27 feet per hectopascal. This means that for every 1 hectopascal drop in pressure, the altimeter will show an increase of 27 feet. Looking at the diagram, we can see an airfield 1,000 feet above mean sea level. If the QFE was 980 hectopascals, what might the QNH pressure be? What we have to do is increase the pressure from the airfield to mean sea level. But by how much? If we know that pressure changes by approximately 27 feet per hectopascal, all we have to do is to find out by how much the pressure changes in 1,000 feet. This requires a simple calculation. 1,000 feet divided by 27 tells us that the pressure change in 1,000 feet is approximately 37 hectopascals. Now we simply add this to the pressure at the airfield to find the QNH. In this example, the QNH will be 980 plus 37, which equals 1,017 hectopascals. Let's try another example. Let's say an airfield 2,100 feet above mean sea level has a QNH pressure of 1005. What will the QFE be? Since the QFE is the airfield pressure, and the airfield is above mean sea level, then we know QFE will have a lower value than the QNH. But how much lower? If we know that in a height of 27 feet the pressure changes by 1 hectopascal, then we can say in 2,100 feet we have a pressure change of approximately 78 hectopascals. Therefore, the airfield pressure will be 927 hectopascals. So far, we've looked at how the altimeter works and how we can best use it to eliminate varying pressure changes along a route and near the ground. The variable subscale and the different pressure settings helped us to do this. However, there is one significant variable which the altimeter cannot cater for: temperature. In our earlier lessons on pressure, we saw that temperature affected the pressure lapse rate. Our altimeter is calibrated to an ISA temperature profile and is unable to adjust for the effect of any deviations away from ISA. Let's recap what we've already learned about how temperature affects the lapse rate and pressure levels. Here we can see that if we cool air down, the pressure levels contract and increase the pressure lapse rate. If we warm the area on the right, we can see an expansion of the pressure levels. Let's fly an aircraft from the area on the right to the area on the left at a constant indicated altitude. We know that to achieve this, the pressure must not change. In other words, we must follow a pressure level. However, in doing so, we are inadvertently following a pressure level that's actually descending. So in reality, we are descending, but the altimeter is not indicating this. Therefore, our true altitude is decreasing, but our indicated altitude is constant. There's a saying which is used to remind pilots of this potential problem. When flying from hot to cold, don't be bold. Or, even more dramatically, cold kills. We can further adapt this to be high, low, high. Flying from high temperature to low temperature, the altimeter will read high. In other words, it overreads the true altitude. We saw the use of high-low-high previously for horizontal pressure changes along route. This temperature effect will reverse if we fly into a warmer region. Notice how the aircraft is in fact climbing away from the ground, but that the indicated altitude is staying constant. This example illustrates the concept of low, high, low. Flying from a low temperature to a high temperature, the altimeter will read lower than true altitude. This temperature effect on the altimeter is important, and we must understand that in areas colder than ISA, our altimeter will overread true altitude. This, of course, only really becomes important when close to the ground, and especially so when a pilot cannot see the ground. His altimeter is not accurately informing him of his true height. So, to provide more accurate indications, we have a formula that enables us to calculate the error. This formula states that, for every 1 degree Celsius deviation from ISA, the error in the altimeter is 4 feet per 1,000 feet. This formula is derived from another formula we saw in the pressure lesson. That formula was telling us the height difference per hectopascal. The best way to explain this new formula is to go through an example. Let's say we have an aircraft that's flying level towards a very tall mast which is shown to be 2,000 feet above mean sea level. The temperature is 0 degrees Celsius. What would the altimeter indicate with QNH set? Firstly, we'll need to calculate the ISA deviation. Remember that at mean sea level, ISA states that the temperature is 15 degrees Celsius, and that it decreases by 1.98 degrees Celsius per 1,000 feet. The temperature at 2,000 feet above sea level, according to ISA, is 11.04 Celsius. The ISA deviation is therefore minus 11.04 Celsius. In other words, the real atmosphere is 11.04 degrees Celsius colder than ISA. From the formula, we see that for every 1 degree deviation we had a 4-foot error per 1,000 feet. But we have an 11.04 deviation. So we multiply 11.04 by 4 feet to give an error of 44.16 feet per 1,000 feet. However, our aircraft is at 2,000 feet, so we must multiply 44.16 by 2 to find the total error in 2,000 feet. Therefore, our altimeter is in error by 88.32 feet. If our aircraft is flying level with this mast, which has been shown to be 2,000 feet above mean sea level, then that must be our true altitude. But will our indicated altitude be more or less than our true altitude? If you remember from earlier, we said that in colder than ISA conditions, the altimeter would overread. Therefore, our indicated altitude would be 2,088 feet. The temperature error in altimetry is important and has led to a number of accidents. To prevent this, information is usually given to provide a landing pilot the necessary details to ensure more accurate calculations of obstacle clearance. Advanced instruments like radio altimeters very accurately calculate the aircraft height above the ground. Unfortunately, these instruments are only useful within 2,500 feet of the ground surface. Temperature errors are not the only errors in the altimeter. There are many more. However, these are outside the scope of the lesson. You will be made familiar with them when you study the altimeter in aircraft instruments.
Throughout this lesson, we are going to investigate temperature and demonstrate its importance to meteorology. Temperature is defined as a measure of how hot or cold a substance is. Temperature can be measured on a variety of scales using many different instruments. The two most common scales we use to measure the temperature of a substance are Celsius and Fahrenheit. The Kelvin scale is rarely used in general aviation meteorology, but you may see it in scientific formulae. However, Celsius is the scale we use throughout the CD-ROM where appropriate. You may be required to convert from one temperature scale to another. To convert Fahrenheit into Celsius, simply minus 32 from the Fahrenheit value and then divide it by 1.8. To convert Celsius to Fahrenheit, simply multiply the Celsius value by 1.8 and add 32. Alternatively, there is a conversion scale for Fahrenheit and Celsius on your flight navigation computer. To convert Celsius into Kelvin, simply add 273. Temperature is measured using a thermometer. In meteorology, thermometers are usually housed in a Stevenson screen, giving a standard exposure to the atmosphere. However, there are many different types of thermometer. The one shown here is a thermograph. Similar to the barograph, it records temperature over time using a rotating drum. For measuring the variation of temperature through the atmosphere, meteorologists use satellite imaging, radiosonde balloonescence, and aircraft reports. All of these have their advantages and disadvantages. Let's now consider the practical implications of temperature in the atmosphere. Energy from the sun, or solar radiation as it is called, has a short wavelength, around 0.15 to 4 microns to be precise. The Earth's atmosphere is almost totally transparent to this incoming shortwave radiation. The incoming energy passes through the atmosphere with little effect. Only when solar radiation encounters clouds or reaches the Earth's surface does it have an impact. Clouds will reflect part of the incoming energy backwards, possibly out to space again. The rest will continue to the Earth's surface. In clear weather, around 85% of the Sun's original energy will reach the Earth's surface. Looking at the right-hand side of the diagram, we can see that some of the radiation is reflected and not absorbed by the Earth. If the surface has a high reflective factor, or albedo, such as snow or ice, a large part of the energy is reflected back up through the atmosphere. The darker the surface, the more of the sun's energy the surface absorbs, and is said to have a low albedo. Here we see different surfaces in order of reflectivity, highest at the top, lowest at the bottom. At the surface of the Earth, the sun's energy has its greatest effect. Here we see a simple close-up view of the process. Incoming shortwave solar radiation, or insolation as it is also known, leads to some evaporative processes of water and ice, but most energy is used in heating the surface on which it falls. The energy that is absorbed is then available to heat the Earth's atmosphere by other processes. The Earth continually radiates energy that it has previously absorbed. It is a relatively long-wave radiation between 4 and 80 microns. The radiation that is emitted warms the air above the Earth's surface. Apart from the ozone layer high in the atmosphere, which we shall look at later, this is the only source of heat energy for the atmosphere, and explains why temperature falls with height. Hence, the atmosphere is primarily heated from below, not from above. The Earth is the atmosphere's main energy source, not the Sun. So what happens to this energy as it is emitted from the Earth's surface? How does it heat the atmosphere? The most important process is where two of the constituents of the atmosphere, water vapour and carbon dioxide, absorb this long-wave radiation from the Earth. This then acts as a heat reservoir for the atmosphere, warming it up. This is the process called the greenhouse effect, and without it, the Earth would cool dramatically. There are other means by which heat is redistributed through the atmosphere. These are conduction, convection, advection, and latent heat release. Let's take a look at these in turn. Conduction is the simple process whereby heat is transferred from one body to another with which it is in contact. This diagram is a simple representation of the temperature change with height through the atmosphere. Notice the lowest layers, which are in direct contact with the Earth, are the warmest. If we look at a typical situation just after sunrise, this is how the temperature profile may look. Throughout the day, as the Earth's surface heats up, it warms the air in contact with it. Only the lowest layers of the atmosphere respond to this heating by conduction. At night, the Earth's surface temperature falls, since there is no incoming solar radiation. Via conduction, the Earth cools the air just above it. Here we see the cooling process and how the lowest layers of the atmosphere respond. This is why a surface temperature inversion can form. Because air is a poor conductor of heat energy, the air at higher levels retains its heat. The air cools at the surface, and this cooling spreads slowly upwards by conduction. The next process we are going to consider is convection. Convection is simply the way in which warmer, less dense air rises. Cooler, more dense air will tend to sink, replacing the rising pockets of warmer air. We see this effect on many days when cumulus cloud forms. This process transfers heat energy up into the atmosphere and is most effective the more active the convection. In fact, with deep cumulonimbus clouds, some heat energy is taken right up to the tropopause. We saw this effect demonstrated very well in the pressure systems lesson when we discussed small-scale depressions. Advection is the horizontal movement of air into another region. The nature of advection may be warm or cold, and can occur at any height within the atmosphere. Nevertheless, it has an impact on the heat distribution of the atmosphere. Here we see examples of warm and cold advection. Finally, let's take a look at latent heat processes. Latent heat has a major impact on the heat distribution of the atmosphere. Here we see water vapour having been evaporated from a moist or wet ground surface. As air rises, perhaps due to convection, the air cools. It may eventually form clouds as the water vapour condenses. This change of state from gas to liquid releases latent heat, which warms the atmosphere around it. Note, however, that downdrafts associated with heavy rain will drag high-altitude cooler air towards the surface, cooling the surface layers. So, we have established that the Sun primarily heats the Earth's surface, which then, by various processes, heats the atmosphere from below. We stated that this is the reason the temperature generally falls with increasing height. The rate at which temperature falls is called the lapse rate. In a uniform atmosphere, this would be a constant value of 1.98 degrees per 1,000 feet of ascent, often rounded up to 2 degrees. Where the temperature is constant through a depth of atmosphere, we describe it as being isothermal. Where the temperature rises with increasing height, we have what is called a temperature inversion. An inversion would typically form at the Earth's surface on a still, clear night in winter, when the ground temperature falls quickly and the air immediately above it cools by conduction. Here's the temperature height graph again. If you remember from the pressure systems lesson, we often get temperature inversions in areas of high pressure. This is where mass descent of air has taken place, resulting in adiabatic warming of a section of the atmosphere. These inversions were called subsidence inversions. Another example of an inversion usually occurs above the tropopause. Here is the temperature profile around that part of the atmosphere. The temperature through the stratosphere shows a steady rise due to the presence of ozone. Ozone absorbs solar radiation and then re-emits heat energy, warming the surrounding atmosphere in the process. Hence, the tropopause is usually one of the coldest points in the atmosphere. Looking at the air temperature near the Earth's surface, usually measured in a Stephenson screen, we see considerable variations both daily and seasonally. The temperature of the air often varies greatly through a 24-hour period. We will look at the main reasons for this in turn. The sun is at its highest at noon, with the maximum incoming solar radiation at that time. However, due to lag, or what's called thermal inertia, the surface of the Earth continues to receive more incoming solar radiation than it gives out. Therefore, the actual maximum air temperature usually occurs some 2 to 3 hours after maximum solar elevation. This effect is greatest over land on a hot summer's day with light winds. Similarly, the minimum temperature time is around an hour to an hour and a half after dawn. Clouds have a big influence on the maximum and minimum temperatures. If you remember from earlier, we said that clouds reflected incoming solar radiation, thereby reducing the insolation. This would reduce the maximum daily temperature. At night, though, the cloud acts in a very different manner. It re-radiates energy back into the layer of air between it and the surface, much like a blanket. This has the effect of making the minimum temperature much warmer than normal. The combined effect is reducing the diurnal variation of the temperature, but the characteristics of the curve are almost the same. Notice how the maximum daytime temperature is lower with cloud cover, and the minimum temperature, occurring just after dawn, is higher with cloud cover. The wind also affects the diurnal variation of the temperature. By day, the effect is to reduce the maximum temperature. This is because turbulent mixing of the lower parts of the atmosphere brings down cooler air from above, mixing it with warmer air near the surface. Wind also reduces the time that air is spent in touch with the ground, lowering the amount of warming that takes place by conduction. At night, the wind holds the temperature up, preventing it falling as low as it otherwise would. Air near the surface cools first by conduction with the ground. Look at how turbulent mixing then brings the warmer, unaffected air down from a higher level, averaging out the temperature through an appreciable depth of the atmosphere. The direction, as well as the speed of the wind, has an effect on the temperature. This is mainly a product of the surface over which air is moving. If wind is blowing from sea to land, or vice versa, the effect on the temperature will depend on the time of day. At night, an onshore breeze will tend to hold the temperature higher because the sea takes longer to cool down and will generally be warmer than the land. Conversely, through the day, a sea breeze will keep the temperature down because the sea takes longer to warm up. We'll examine local winds at a later stage in more detail. There is, of course, a large temperature variation across the surface of the Earth. There are many factors involved with this, and we shall now take a look at the main ones. Take a look at this diagram. You should be able to see that when considering a unit cross-section of energy from the Sun, the same amount of energy is spread across a greater area at higher latitudes than at the equator. Therefore, any single point at high latitude will receive less energy from the Sun than a point at lower latitude. It is interesting to note that compared to the distance between the Sun and the Earth, the slightly greater distance between the poles and the Sun, compared to the equator and the Sun, is negligible. Each year, on March 21st and September 21st, the Sun is directly over the equator. These occasions are known as the vernal and autumnal equinoxes. On June the 21st, the Sun is directly over the Tropic of Cancer, and the Northern Hemisphere enjoys its summer season. Similarly, on December the 21st, the Sun lies directly over the Tropic of Capricorn, and the Southern Hemisphere is in its summer season. As you can see, this affects the amount of radiation reaching the Earth's surface, and so has a direct effect on the temperature in the lowest layers of the atmosphere. The sea surface temperature takes a long time to react in terms of warming and cooling. Here we see the fact that there is very little diurnal temperature variation of the sea when compared to the land. Look at how the variation over the sea is different to that over land. This is because the sea has a large specific heat capacity. This means that the sea requires more energy to raise the temperature by 1 degree than the land does. This differential of the temperatures over land compared to sea is the cause of such things as sea breezes, where air is coming from the sea to the land, and land breezes, where air is coming from the land to the sea. The origin of the air mass is an important factor when considering temperature. When air is static over a region for a period of time, it gathers the properties of the underlying surface. We look at this in detail later on in the air mass lesson. But it is enough to say at this point that air coming from tropical areas will raise the temperature, whereas air coming from polar areas will lower the temperature. The topography of the land has a major influence on the temperature of the air. At night, air in the bottom of the valley tends to remain rather static due to the sheltering effects of surrounding higher ground. This air, therefore, has the opportunity to cool. Colder air also tends to drain towards the low-lying areas. This is why fog tends to form in valley bottoms on still, clear nights. Here we see the situation on a typical day. It is different from night time, as you can tell. Hilltops tend to be cooler than lower-lying areas during the daytime. This is because air comes in from the sides and has little contact with the ground, and hence little opportunity to warm up by conduction. There are also many other effects the topography can have on temperature, such as valley winds and the Föhn effect, but we shall look at these in detail, along with the sea and land breeze, in the lesson on winds. As you can see, there are many important factors about temperature which affect aviation. The principal one is how the temperature relates to the icing risk for aircraft, and we look at that in detail in the lesson on icing. Through this lesson, we have looked at how the atmosphere is heated by terrestrial radiation, including conduction, convection, latent heat, and advection. Also, the idea of lapse rates, and how temperature usually falls with height through the troposphere. Through this lesson, we are going to look at humidity, and in particular, issues surrounding water vapour. The substance of water has three well-known states or phases: the solid state, called ice, the liquid phase, simply called water, and finally the gaseous state, called water vapour, which of course we usually cannot see. Dry air is defined as a body of air with no moisture content at all. In reality, this does not occur in the atmosphere. When any amount of water, in vapour form, is present in a body of air, the air is defined as being moist. Looking at the diagram, we can see a parcel of dry air with no water vapour, and a moist parcel of air with water vapour. The presence of water vapour in the atmosphere has a major impact on the behaviour of air. However, the concentration of water vapour varies greatly, both in space and time. It is generally found in such small quantities that it is not even listed as a trace gas, but yet its presence impacts on us greatly. Without it, there would be no weather. Uniquely, water can be found in the atmosphere in all of its three states. One of the major impacts water has on our atmosphere is when it changes from one phase to another. During these changes, energy is transferred in different ways. This energy is known as latent heat. Latent heat, or hidden heat as it is sometimes called, is the quantity of heat released or absorbed when a substance changes from one phase to another. On the way up from the solid state through liquid to gas, latent heat is absorbed, whilst on the way down from gas to solid through liquid, latent heat is released. Let us see what happens when we change state from solid to liquid, in other words, during melting. As we heat the solid, it will start to melt. Energy, in the form of latent heat, is then absorbed from the surface and then stored in the liquid. Just as we saw latent heat being absorbed into the water when it changed state from solid to liquid, we shall now see the same occurring when we change state from liquid to gas. This is known as evaporation. During evaporation, latent heat energy is absorbed from the surface and stored in the water vapour. Evaporation from a water surface will occur at any temperature above absolute zero, minus 273 degrees Celsius. But the rate of evaporation increases as the temperature increases. This is because as temperature increases, the water molecules have more energy and are more likely to change state. Looking at the diagram, we can see that evaporation from the water surface is adding water vapour to the air. However, for a particular temperature, there is a maximum amount of water vapour a body of air of unit volume can hold. So, as evaporation continues, the air above the surface will contain more and more water vapour, and may eventually reach its maximum holding capacity. When this is reached, evaporation will cease. The air above the water surface is said to be saturated. It can hold no more water vapour. To recap then, if we continually add water vapour to a parcel of air, it will eventually become full or saturated. We have established that one way we can make air saturated is by evaporating water into it until it is full of water vapour. However, there is another method of achieving this. If we cool air down, the space between air molecules decreases, and therefore there is less space for water vapour to fit. The opposite is true when we warm air up. Warm air has more spaces between the molecules and can hold more water. So, if we have a parcel of air that is partially filled with water vapour and then cool it down, the air will eventually reach a point where it is holding as much water vapour as it can. Now the air has become saturated. Condensation is the reverse of evaporation. It is the phase change from vapour back to liquid. If you remember, the water vapour had a lot of stored latent heat. So, when it then condenses and changes into water again, it releases this heat back to the surroundings. Again, we can appreciate this when we have been burnt from steam. The steam is hot anyway, but when the steam condenses onto our skin, even more heat is given to us, and we feel even more pain. As we have seen, condensation is said to occur when water vapour changes state into visible water, like dew, clouds and fog. But this process is actually quite complex. For condensation to occur, we need minute particles in the atmosphere for the water to form around. These are called condensation nuclei, and mainly consist of salt particles put into the atmosphere over the sea. There are other condensation nuclei, such as pollutants from industrial sources, forest fires, or volcanic eruptions. If no condensation nuclei are present, air will tend to become supersaturated, and hence have a humidity of greater than 100%. When the temperature of water drops below 0 Celsius, it generally begins to freeze, i.e. change from liquid to solid. Remember from earlier in the lesson that this involves the release of latent heat. Here we can see the heat being given up to the surroundings. In a similar manner to condensation, freezing usually requires the presence of particles. In this case, they are known as freezing nuclei. So as the temperature of the droplet falls, if there are particles in the water, the droplet will freeze. However, if they are not present, then when the temperature falls below 0, it will not freeze. These are known as supercooled water droplets and are very important in aircraft icing. There are two other phase changes that we need to mention. These are less common in the atmosphere than condensation or evaporation, but nevertheless are important. When water goes straight from the solid to vapour state, we call it sublimation. Strictly speaking, when water goes from vapour to the solid state directly, it is called deposition, but in meteorology, this change is also called sublimation. Note that both of these phase changes miss out the liquid phase. Sublimation from ice to water vapour absorbs latent heat, and sublimation or deposition from water vapour to ice releases latent heat. In meteorology, it is vital to know how much moisture the air contains at any one point. We can do this using a hygrometer, also known as a psychrometer. Here we see a diagram of one type which uses a wet bulb and a dry bulb arrangement. If air is unsaturated, water will evaporate into it from the muslin, and latent heat will lower the temperature of the wet bulb. If the air is saturated, no water will evaporate and the two thermometers will read the same. The wet bulb temperature is defined as the lowest temperature air will fall to by evaporating water into it at constant pressure. The difference between the dry bulb and the wet bulb decides how moist or humid the air is. The closer they are, the more humid the air is, and vice versa. From these two readings, many values can be calculated, including the dew point, vapour pressure, relative humidity, and humidity mixing ratio. We shall now look at this in a bit more detail. The dew point of the air is the temperature to which air must be cooled at constant pressure to reach saturation. Do not confuse this with the wet bulb temperature, they are different things. The dew point of the air will only change if the amount of water vapour in the air changes. Remember when we talked about the difference between dry and wet bulb temperature readings? Well, in a similar manner, the difference between the dry bulb temperature and the dew point signifies the humidity of the air. When the dry bulb temperature equals the dew point, there is 100% humidity or saturation, hence cloud or fog will form. If the dry bulb temperature and the dew point are many degrees apart, the air is relatively dry. In fact, at saturation, the dry bulb, wet bulb, and dew point temperatures are all exactly the same. The dew point lapse rate varies enormously on any one day, with large changes in both spatial and temporal contexts. But on average, the humidity mixing ratio lapse rate is 0.5 degree per 1,000 feet. A simple rule of thumb is that the difference between the dry bulb temperature and the dew point is equal to 100 minus the humidity divided by 5. Here we see two boxes containing moist air. However, one is more moist than the other. In the atmosphere, each constituent gas that makes up the air exerts its own pressure. It is the sum of these pressures that actually makes up the total atmospheric pressure that we often use in aviation. Water vapour is the same. It is a gas. Therefore, it exerts its own pressure, and this we refer to as the vapour pressure. In our diagram, the box on the left has a lower vapour pressure than the one on the right. Therefore, the pressure being exerted on the walls of the container by the water vapour is less. Let us consider an enclosed box, half filled with water, with air filling the rest of the box. Initially, the air above the water is unsaturated. There will be a value for the vapour pressure. However, evaporation will immediately start to take place. If we left this box alone for long enough water will have evaporated from the water surface for the air to become saturated. At this point, evaporation will stop, and the vapour pressure will also cease to rise. This maximum value of the vapour pressure occurs at saturation, and is called, unsurprisingly, the saturation vapour pressure. We are now going to talk about humidity and its measurement. We can reference humidity with two specific terms: relative humidity and absolute humidity. Relative humidity is the percentage degree of saturation. Or put another way, it is the amount of water vapour a body of air actually contains, relative to the maximum amount it could hold, expressed as a percentage. A relative humidity of 100% is saturation. Absolute humidity is the mass of water vapour contained in a unit volume of air. It is expressed in terms of grams per metre cubed. Humidity mixing ratio, or HMR, is a similar property to absolute humidity, in that it is a measure of the amount of water vapour contained in a sample of air. But whereas absolute humidity is the mass of water vapour in a unit volume of dry air, the humidity mixing ratio is the ratio of the mass of the water vapour to the mass of the dry air. It is expressed in grams per kilogram. In temperate latitudes, the HMR value lies somewhere between 5 and 50 grams per kilogram. In unsaturated air, the HMR remains constant with increasing height, whereas pressure and temperature decrease. Saturation mixing ratio, or SMR, is simply the HMR when the air is saturated. That is all for the humidity lesson. We have looked in detail at water and its phases or states, and also the practical implications of changes between these phases. As we have seen through this lesson, water plays a major part in the atmosphere and the weather, despite the relatively small quantities in which it exists.
Throughout this lesson, we are going to look at adiabatic processes and stability within the atmosphere, and how they are uniquely intertwined. In aviation meteorology, you'll often hear the shortened term adiabatics used. This simply means the whole concept of adiabatic processes. The idea of an adiabatic process is a theoretical one that we introduce in order to understand what's happening within the atmosphere. Put simply, an adiabatic process is one which involves no transfer of energy into or out of the system that we're considering. This is a reasonable thing to do, since air is a poor conductor, and so heat energy doesn't want to flow through a section of the atmosphere very easily. There are two distinct processes: adiabatic warming and adiabatic cooling. To explain these, let's now consider a parcel of air sitting on the surface of the Earth. If we lift this parcel of air into a region of lower pressure, then it will expand. Remember, this is an adiabatic process, so no energy leaves or enters our parcel. This expansion happens because the pressure within the parcel wants to equalize itself with the surrounding pressure. The expansion process uses up some internal energy of the parcel, hence, as the parcel of air rises, it expands and the temperature actually falls. This is known as adiabatic cooling. The opposite is also true if we look at a parcel of air that is forced to drop to a lower level within the atmosphere. As the surrounding pressure increases, it forces the parcel to contract. This increases the internal temperature of the parcel. Therefore, we now have adiabatic warming. So, air moves around within the atmosphere. As it rises, it expands and cools adiabatically, and as it descends, it's compressed and so warms adiabatically. Think of a bicycle pump. As the air is compressed within the pump, it heats up, making the actual pump chamber quite warm. This is almost exactly the same process that occurs within the atmosphere. The rate at which air cools or warms, as it is forced to rise or fall, depends upon the moisture content of the parcel of air. This is called the adiabatic lapse rate. If we first consider air that is dry or unsaturated, then the maximum rate at which the temperature falls is 3 degrees Celsius per 1,000 feet of ascent, or 1 degree Celsius per 100 meters. This is called the dry adiabatic lapse rate, or DALR for short. Now let's think about the moisture content of our parcel of air, in the form of water vapor. The presence of water in the atmosphere complicates things significantly, and it's most important to understand the processes that are involved. Air can hold only a limited amount of moisture or water vapor before it reaches saturation. Warm air can hold more water vapor than cold air. This is due to the greater distance between air molecules in the warm air, creating more room for water vapor molecules. If warm, unsaturated air is cooled, it eventually reaches a point at which it becomes saturated. The water vapor will at that point start to form water droplets or condense out. This condensing out of the water vapor has one very important effect. It releases what is called latent or hidden heat. So we say that the process of condensation releases latent heat. Let's consider our parcel of warm, dry air again. If we force it to rise, the temperature will fall at the dry adiabatic lapse rate, or DALR, of 3 degrees Celsius per 1,000 feet, or 1 degree Celsius per 100 meters of lift, as we stated earlier. When the temperature falls to a certain level, condensation will take place. The water vapor, previously invisible to the naked eye, becomes visible. In other words, clouds will form. If the process of lifting and cooling continues, then more vapor condenses, releasing more latent heat. The release of latent heat has the effect of slowing down the rate of cooling. Therefore, the lapse rate in saturated air, that is, cloud, will be very different to that of unsaturated air due to the release of latent heat. This new lapse rate is called the saturated adiabatic lapse rate, or SALR, and is, on average, 1.8 degrees Celsius per 1,000 feet of lift, or 0.6 degrees Celsius per 100 meters. This is the rate at which saturated air will cool if forced to rise. The SALR is not constant through the troposphere. It reduces the higher up you go, and in fact, the saturated adiabatic lapse rate is almost exactly the same as the dry adiabatic lapse rate in the upper reaches of the troposphere. This is because the amount of water vapor that is required for saturation reduces at lower temperatures. It therefore follows that the amount of latent heat that is released also reduces as a parcel of air rises. The most commonly used average lapse rate of the SALR is 1.8 degrees Celsius per 1,000 feet, or 0.6 degrees Celsius per 100 meters. However, the actual rate varies from around 1.2 degrees per 1,000 feet at 26 degrees to 2.2 degrees when the temperature is around minus 10 degrees. Now we're going to look at the issue of stability. The stability of air depends upon two things: its temperature and moisture content, or humidity. Air is stable if it returns to its original level after being given an initial movement upwards. Thus, if a parcel of air is surrounded by air which is the same temperature as our parcel, the conditions are stable. The parcel will merely want to stay where it is. If it's given a push upwards, it will settle back to its original position. Note that the air is stable when both saturated and unsaturated conditions are considered. Air is unstable if, after an initial movement upwards, it continues to rise. In other words, it's buoyant. This happens when the parcel of air finds itself surrounded by cooler air. We now have three different lines on our diagram, and we're going to use these to explain stability. These lines are the DALR, the dry adiabatic lapse rate, the SALR, or the saturated adiabatic lapse rate, and the ELR, the environmental lapse rate, which is the actual prevailing conditions at any one point in the atmosphere, since air is rarely completely dry or completely saturated. Note, though, the ELR is not fixed. It is very variable and will be different from day to day. The position of the ELR in relation to the other two lines, namely the DALR and the SALR, determines how we classify the stability of the atmosphere, as you might expect. Because we are considering both the DALR and SALR, the temperature and the humidity have a say in this classification. So, if the ELR is greater than the DALR, then the atmosphere is defined as being absolutely unstable. This situation is not common within the atmosphere and only happens just above the surface on sunny days. If a parcel of warm air is rising, it's warmer than its surroundings, the ELR. It will continue to rise, expanding and cooling as it goes until it reaches the same temperature as its surroundings. Now let's look at the opposite case. If we consider this part of the ELR, then the situation is defined as being absolutely stable. This is when the ELR, the environmental lapse rate, is less than the SALR. Therefore, the parcel of air will never be warmer than its surroundings, and so will stay in the same approximate position. The final scenario we must look at is in this part of the diagram. So the ELR is said to be conditionally unstable if the lapse rate is less than the DALR, but greater than the SALR. This is an important point about stability, which is sometimes not fully understood. The air is stable if dry, but unstable if saturated, and the situation is then called conditional instability, because the stability depends upon whether or not the parcel of air is saturated or unsaturated. There are two final scenarios we must look at which are linked. When the air is saturated and the ELR happens to fall on the SALR, then the atmosphere is said to have neutral stability. Similarly, if the air is unsaturated and the ELR happens to lie along the DALR, then the atmosphere is again said to have neutral stability. So far in this lesson, we have looked at how dry and saturated air behave when forced to rise within different environmental lapse rates. Using this graph, we saw that the value of the ELR and its position helped us decide the stability of the atmosphere. Now let's consider what weather you will encounter with the different types of stability. First, let's look at an unstable atmosphere situation. In this scenario, our parcel of air is warmer than its surroundings and can be described as buoyant. It will therefore naturally want to rise to a higher level, expanding and cooling as it does so. This situation is associated with convective-type cloud, cumulus or cumulonimbus. This type of atmosphere is quite bumpy or turbulent, especially in the clouds themselves. With convective cloud, we get our vigorous updrafts within clouds which support large water droplets. This has two effects. It will therefore naturally want to rise to a higher level, expanding and cooling as it does so, but is usually rain, hail, or snow, or perhaps a mixture of all of these. It's very important to know that there's a significant increase in the icing risk within these convective clouds. We'll look at this in detail later, but note at this point that this is the IKO symbol for moderate icing, and this is the one for severe icing. The icing risk for aircraft in large cumulus cloud, whose temperature is low enough, is classed as moderate, occasionally severe. The icing risk associated with cumulonimbus clouds is always severe. One other thing to consider is the visibility. In an unstable situation, there is lots of overturning of the air, creating a great deal of mixing. This spreads any airborne pollutants through a great depth of the atmosphere. Therefore, the visibility is usually very good within an unstable air mass. The exception, of course, is when a heavy shower is occurring. Under precipitation, this visibility temporarily reduces, and in snow showers can be extremely poor, often as low as 500 meters. Now let's consider the weather when we have a stable atmosphere. Our parcel of air in this situation does not inherently want to rise when nudged upwards. If forced to rise, the parcel of air will cool more rapidly than the surroundings. This makes the parcel of air denser and heavier than its surroundings. Therefore, when the lifting force is removed, the parcel will want to return to its original position. The atmosphere is said to be stable when this condition exists. That is, it's very resistant to vertical uplift. The types of cloud we should immediately associate with this type of atmosphere are clouds of relatively little vertical but large horizontal extent, that is, stratiform cloud. Note that these sizes are relative. Stratiform clouds can be quite deep vertically, say 3,000 to 5,000 feet, but then usually have a horizontal extent of several kilometers or tens of kilometers. Due to the lack of great overturning within the atmosphere, there is usually little turbulence within a stable air mass. Due to the vertical motion of air, the precipitation associated with stable air masses tends to be of rain or drizzle, or perhaps snow if the temperature is low enough. It's characterized by its persistence and intensity, usually lasting for a longer period of time. That is, it's quite persistent with a slow onset and cessation, rather than sudden, which is often the case with showers. The precipitation is usually made up of smaller drops, as the moderately rising air cannot support water droplets of any great size, hence lighter rain, drizzle, or snow. Because of the absence of large supercooled water droplets, the icing risk is usually light. There are two big exceptions to this situation, however. The first one is when the temperature structure is just right to give freezing rain or drizzle. This is a serious hazard, and is also called ice rain or drizzle. We shall look at this in detail later, but in non-summer months, if the temperature is reasonably low, always spare a thought for freezing precipitation when flying ahead of a warm or occluded front. The other situation when the icing risk can be significantly increased is again ahead of a warm or an occluded frontal system, but this time over high ground. As the frontal system approaches the high ground, the lifting of the air is greatly enhanced, forcing a large number of water droplets higher into the atmosphere. This can make the icing risk moderate, occasionally severe, especially in nimbostratus cloud. With a stable atmosphere, there's little vertical movement of air. We find that airborne pollutants tend to stick in the layer where they are initially introduced. As the Earth's surface is the source of most pollutants, the visibility low down in the atmosphere is often moderate to poor in a stable air mass. This completes the lesson on adiabatic processes and stability, but both of these concepts will crop up again in other areas of aviation meteorology.
In this lesson, we'll look at the phenomenon of turbulence and how it is created within the atmosphere. More importantly, we'll examine its impact on aviation and how we can locate it and avoid it. Turbulence strictly means a disturbed state, but in aviation it means disturbed or rough air. For the purpose of a definition, we will consider turbulence to be variations in the wind along the aircraft's flight path, of a pattern, intensity and duration that disturb the aircraft's attitude about its major axes, but do not significantly alter its flight path. To simplify this statement, we can say that turbulence does disturb the aircraft's attitude, but the aircraft can still maintain its flight path. Wind shear is similar to turbulence, but far more severe. It is not rough air, but air that has marked variations in speed and/or direction. A definition of wind shear is variations in the wind's speed and direction along an aircraft's flight path of a pattern, intensity and duration that displace the aircraft abruptly from its intended path, such that substantial control action is required. Strictly speaking, wind shear is a rate of change of the wind velocity in space, and is to be considered a vector. Vertical wind shear is the change in the wind speed and/or direction with height. The diagram shows what this might look like. The bottom of the tower is exposed to a very different speed and direction than the top. Vertical wind shear is usually measured in knots per 100 feet. Horizontal wind shear is the change in the wind speed and direction with horizontal distance. Again, the diagram shows this using a runway to illustrate the situation. The direction and speed at one end of the runway is very different to that at the other end of the runway. Horizontal wind shear is usually measured using knots per 1,000 feet. We will discuss wind shear later in the lesson, but for now let's return to turbulence, which was disturbed or rough air. One of the most common causes of turbulence is the surface over which the airflow is moving. The layer of air that is disturbed is known as the friction layer. Above this, the airflow is unaffected by the surface. The boundary of the disturbed surface flow and the undisturbed upper flow is called the friction level. This disturbed air near the surface is created in two ways. Mechanically, by objects like trees, hills and buildings, and thermally, through the effect of warm air rising. We call these effects mechanical or thermal turbulence, respectively. If we first look at mechanical turbulence, we can see that the greater the physical obstruction, the greater the depth of airflow that is disturbed. This is common over land, especially around hills and towns. Notice that the friction layer is thicker and that the friction level is higher. Thermal turbulence is slightly different though. Some areas of the Earth's surface will be warmer than others, and will have greater amounts of warm air rising above them. This again acts as a disturbance to horizontally moving airflow. Notice also that the greater the thermal currents, the thicker the friction layer, and the higher the friction level. This would be common with areas of low albedo, like rocky areas and fields, where the surface is absorbing large amounts of solar radiation. This thermal effect is extremely important to glider pilots, and they will examine the land carefully, not only for physical objects giving vertical currents, but more importantly for areas giving marked thermal up currents. As a result of the thermal effect, we should be able to notice a diurnal change in the friction layer and the friction level. When the land is at its coldest, usually just after sunrise, the friction level will be at its lowest. Whereas during the afternoon, when the land is at its warmest, the friction level will be higher. However, on average, the depth of the friction layer is only a few thousand feet above the surface, usually 2,000 to 3,000 feet. But as we have seen, this will vary. It is not just near the surface where we find disturbed air. A very common place is within and surrounding significant cloud developments. Looking at the diagram, we know that the cloud was created by air rising and cooling. Within the cloud, we can see significant vertical currents of air. These will disturb the general horizontal flow of air, creating turbulence. Clouds therefore present to the pilot a very good visual clue to the movement of air and the potential hazard. For this reason, cumuliform clouds, which are vertically developed clouds, are treated with caution in aviation. Cumulonimbus clouds are the most visually obvious in terms of their turbulence capability, and turbulence around these clouds is always severe. A fact not commonly emphasized to pilots is that we don't just find turbulence within the clouds themselves. Looking at the diagram, we can see the turbulent currents close to the areas of cloud development. However, turbulence from these systems can still be experienced at some distance from the cloud development. If we now consider the bigger picture, we can identify downdrafts at quite some distance from the cloud. These currents can also cause turbulence, and again, very large cloud development, like cumulonimbus, must be treated with extra caution. There is one added concern with large cloud developments, particularly the cumuliform type. When precipitation falls from clouds, it tends to drag air down with it, creating downdrafts within and underneath the cloud. This situation will aggravate any turbulence created already from the rising air, since now we have air going down as well as up. If the amount of air descending from the cloud is significant enough, then a phenomenon known as a microburst or macroburst is experienced. In some countries, these are sometimes called cloudbursts. These will be discussed in detail in the lesson on thunderstorms, but suffice to say, these present a major hazard to aviation. When the air descends beneath the cloud, it may come into contact with the ground and then spread out. Because of the very large changes in the direction and speed of the wind, both vertically and horizontally, this gives rise to very dangerous wind shear. There are many causes of wind shear in the atmosphere. In fact, whenever a pilot sees evidence of an abrupt change in wind speed or direction, he should expect to encounter the effects of wind shear, for example, around surface troughs or ridges, particularly those associated with fronts. In the diagram, we can see a location in the northern hemisphere, which is about to experience the passage of an active cold front. The initial wind direction is from the southwest, but as the front passes, the wind direction changes quite rapidly to flow from the northwest. This rapid change in direction will lead to wind shear, and pilots need to be aware of changing wind conditions with the passage of active fronts. We also find significant troughs and ridges in the upper atmosphere. Here, although the winds tend to blow parallel to the isobars, once again, when looking along the trough, we can see substantial changes in direction. However, unlike the cold front near the surface, these areas seldom have the visual clue of clouds to aid the pilot. As a result, these areas of turbulence are called clear air turbulence, or CAT for short. There is one very significant place where clear air turbulence can be found. In the upper atmosphere, we have narrow bands of fast-moving air called jet streams. The speed of these jets of air is frequently between 100 and 200 knots, and can reach 400 knots in rare circumstances. The turbulence or wind shear is not within the jets themselves, but rather around their edge. Surrounding the edge is a zone where the speed changes very rapidly across a short distance, causing extensive turbulence. On the diagram, we can see a cross-section of a typical jet stream. Notice the jet itself is located within the warm air, and the clear air turbulence is located to the side of the jet that faces the cooler of the air masses. The black lines are isotachs, which are lines joining places of equal wind speed. Notice the speed in the centre, and more importantly, notice how close the isotachs are on the cold side of the jet. This shows the rapid change in speed, and is where the clear air turbulence is most likely to be found. These areas are very important to aircraft operating at high altitudes, and as such are shown on significant weather charts issued to aircraft operators. This is an example of a chart showing a CAT area surrounding a jet stream. These charts will be discussed and examined later in the weather briefing section, under medium and high-level significant weather charts. The effect of horizontal airflow over mountains and hills creates a very unique phenomenon. Looking at the diagram, we can see a mountain being exposed to horizontal airflow from the left. As the air flows over the mountain, it starts to oscillate in a wave-like pattern. These oscillations are known as mountain waves, lee waves, or standing waves. However, to create these oscillations, certain conditions must prevail in the atmosphere. Firstly, the air must be very stable. Otherwise, the airflow when reaching the mountain would rise vertically and destroy the oscillation pattern. More importantly, though, it is the layer of air at, around, or just above the mountain ridge that must have absolute stability. Another condition which must be met is that the wind speed at the level of the ridge must be greater than 15 knots and increase with altitude. The direction of the wind in relation to the mountain's orientation is another crucial factor. The winds must flow within 30 degrees either side of the perpendicular. The diagram shows an example of a mountain range aligned north-south. The direction of airflow that's needed to help create the mountain wave must either be from the left, between 240 degrees and 300 degrees, or from the right, between 060 degrees and 120 degrees. When all these conditions are met, the mountain wave will be created. Fortunately for pilots, these oscillations may become visual. Let's take a look at one of the crests downwind of the mountain. Here we can see air rising on one side and descending on the other. This is important. When the air is forced to rise, it will cool adiabatically, and if sufficient moisture is in the atmosphere, condensation may take place and cloud will form. However, when the air is forced to descend on the other side of the crest, it warms adiabatically, and any cloud dissipates. Notice the shape of these clouds. Their lens-like shape has led them to be called stratocumulus lenticularis or altocumulus lenticularis, or for short, just lenticular cloud. Here are typical examples of such clouds. Their shape can appear odd and unusual, leading some observers to mistake them for UFOs. There are other visual clues for the pilot. One of these is the type of cloud that shrouds mountains, making it difficult for the mountains to be seen from the air. These clouds are called cap clouds. A famous example of a cap cloud can be found on Table Mountain in Cape Town, South Africa. These clouds are created by the air cooling adiabatically when forced up onto the top of the mountain. There is one other cloud that is probably the most significant, since it implies the location of the most severe turbulence. If we look at the flow of air underneath the first wave crest, we can observe a circular rotation of air. This zone is the most dangerous, since the wind is changing direction constantly in a very confined area. The clouds that develop here are called rotor clouds or roll clouds. As was mentioned earlier, clouds are the visual clue to what is happening to the airflow and also the possible location of turbulence. But don't assume that without the rotor cloud or lenticular cloud that there is little or no turbulence. There most certainly can be. So, how can we recognise a potential situation for the creation of standing wave activity? Firstly, expect it whenever you cross mountain ridges and hills, especially in windy, stable conditions. Examine your route and identify areas where high ground or mountains exist. Get the forecast charts for wind directions and speed with altitude. Then compare these to the locations on your route where there are mountains or high ground. Since we know the turbulence is downwind of the mountain, and especially within the rotor zone, when flying close downwind of mountains, do not fly below mountain level. In fact, try and avoid the mountain vertically by the highest margin your aircraft and operational parameters will allow. If you have to penetrate the rotor, disengage the autopilot, fly at turbulent penetration speed, and let the aircraft ride the turbulence. Fighting the aircraft and the atmosphere may cause damage to the aircraft structure. Enter and exit the system using the shortest possible route. Never initiate turns. These will give greater G-loads and reduce the aircraft's performance envelope significantly. The most important thing to remember is, never fly downwind, parallel to the mountain, below ridge level. That's where the rotor zones are. There is another situation in the atmosphere that can give rise to turbulence and wind shear. In the lesson on temperature and pressure systems, we said that there may be times when we can experience temperature inversions. If you remember, inversions are where temperature increases with altitude. If the temperature inversions are strong enough, then as a result of the changing density, we can get significant changes in wind direction and speed through the inversion. This leads to wind shear, and as pilots, we need to be made aware of them. If the temperature at 1,000 feet is 10 degrees Celsius higher than at airfield level, then an MTI is issued. MTI stands for Marked Temperature Inversion. If you're told that there is a marked temperature inversion at an airfield, you must expect turbulence or wind shear on the approach or takeoff phase of flight. Strong inversions and MTIs are very common over land at night, within high pressure zones where the ground can cool rapidly. Turbulence of any kind is something we wish to avoid. It is especially dangerous to aircraft on the approach or landing phase of flight, since the aircraft is at low speed, low altitude, and is experiencing high amounts of drag. Fly with great caution and respond promptly to turbulence, and monitor your airspeed closely. Let's now look at how we actually report turbulence. The table shown here relates to the three levels: light, moderate, and severe. Each intensity is described using both aircraft reactions and occupant reactions. Looking at moderate turbulence, we can see that this will be reported any time that indicated airspeed fluctuates irregularly between 15 to 25 knots, and G changes of 0.5 to 1 G are experienced. Notice, though, that the aircraft remains in positive control at all times. Looking at the reaction of the occupants, we would report moderate turbulence any time passengers feel definite strain against the seatbelts, if objects are dislodged, and food service and walking is difficult. Before we finish, let's briefly examine severe turbulence. Notice that indicated airspeed fluctuations and G changes are far greater than that for moderate turbulence. And more importantly, the aircraft may be momentarily out of control. Because this situation is very serious, immediate diversion is necessary. Finally, examine the table and note down the differences between the various intensities. Remember, any time your aircraft is exposed to moderate or severe turbulence, it is compulsory by law to report the incident. Provide as much detail as possible, including location, intensity, time, and aircraft type. The report can be relayed to the air traffic controller if there is time, or alternatively to the nearest Met Office in your area. This helps with future forecasting, but more importantly, informs other pilots of the problem. Through this lesson, we are going to look at wind, primarily within the first few thousand feet of the surface. We will examine what creates wind, what the forces involved are, and how these change as the wind interacts with its environment, particularly the surface over which it flows. What is wind, though? Put simply, it is the motion of air over the surface of the Earth. More particularly, though, it is the sustained horizontal flow of air over the Earth. On a large scale, this flow is very closely related to the varying horizontal distribution of pressure, namely high and low pressure zones. The essence of this lesson will look at this relationship in considerable detail. Firstly, though, let's examine the measurement of wind and its units. Wind is usually represented as a velocity. Velocity is a vector factor, incorporating both direction and magnitude. So wind velocity gives both wind direction and wind speed. Let's take a look at direction. The direction of movement of any subject is usually given in degrees from north. This scale starts from 0, which is north, all the way through to 360 degrees, which is another way of expressing north. Direction is referred to not as the heading of the wind, but rather where the wind is coming from. For example, a wind blowing towards the east is given a direction from the west, and would therefore be shown as having a direction of 270 degrees. A wind blowing towards the north, in other words, coming from the south, would be shown as having a direction of 180 degrees. Changes in the direction of the wind are expressed using the terms backing and veering. A wind that is veering is changing direction in a clockwise manner. For example, a wind that was 090 degrees and is now 170 degrees would be described as veering. A wind is said to be backing if the direction change of the wind is anti-clockwise. For example, a wind that was 180 degrees and is now 045 degrees would be described as backing. However, we have a true North Pole and a magnetic North Pole. The problem is that these are not in the same geographical location. Traditional meteorology has little concern for magnetic north, and therefore wind direction is referred to true north. However, in-flight headings are referenced to the compass, which uses magnetic north. Most wind direction given by meteorologists will be referenced to true north. When using such wind directions, be careful to adjust them using the relevant variation which allows the calculation of magnetic north. There are rare occasions when the reported winds are given as magnetic wind directions and not true wind directions. These are typically whenever wind is reported by an air traffic controller from a tower and in the Recorded Aerodrome Terminal Information Service, or ATIS. If you remember, wind is reported as a velocity, giving both direction and speed. The standard unit of speed is the metre per second. However, this is mainly confined to scientific and theoretical use. More generally, the unit adopted for operational purposes in aviation is the knot. 1 knot is 1 nautical mile per hour. The official ICAO abbreviation for use in aviation is KT. Shown here are the conversion factors between the various units of wind speed, namely knots, meters per second, and kilometers per hour. A wind scale to describe speed was introduced and devised by Admiral Beaufort for use at sea. An adapted version for use over land is shown here, and is often used by meteorological broadcasters today. Measuring wind velocity is quite simple. The most widely used instrument is the cup generator and wind vane, which is shown here. The three cups capture the wind, and as a result, they will rotate about a spindle. The rotation of the cups drives a sensitive electrical generator. The greater the wind speed, the greater the voltage generated. The generator moves the pointer around a dial graduated in knots. The direction of the wind is measured by a remote transmitting wind vane. This simply wants to turn into the wind and offer the least resistance to the airflow. Until recently, these instruments only provided instantaneous readings, but now it is more common for a computer processor to average out readings, usually over a period of 2 to 10 minutes. There is also a requirement to record details of any gusts or lulls in speed. These instruments are used around airfields to calculate the approximate surface wind velocity for aircraft either taking off or landing. The definition of the surface wind is one that blows at approximately 10 metres above ground level. The reason for this is that wind velocity changes dramatically with height, and the very near surface velocity can be completely different from that a few metres above the surface. Consequently, these instruments are placed 10 metres above ground level and free of any nearby obstacles that may unduly disturb the flow of air and give misrepresentative readings. On some weather charts, you may see wind speed and direction being coded. Shown here are a few examples of how these are presented. Let's take a look at example number 1. The circle denotes the point of observation or the location of the reading. The direction is shown by a straight line coming from the circle. This line points towards the direction from which the wind is blowing. Shown here is a wind from 270 degrees. In other words, a westerly wind. The wind speed coding is attached to the line emanating from the circle. A thin straight line or feather represents 10 knots. A short line or feather represents 5 knots. The triangle shows a speed of 50 knots. In this example, we read the speed as 65 knots. Example number 2 shows a southerly wind direction of 180 degrees and a speed of 25 knots. Now that we have learnt some fundamentals about wind, including speed, direction, units and coding, let's examine some specific winds and the forces involved.